Eric, I guess it's time to start.
Okay, great. So, good morning to all participants in the American. Good afternoon for European colleagues. On behalf of the organizing committee, welcome to the 33rd edition of the International Conference on Science and Technology Complex Fluids, also known as the Complex Fluids in Mexico. My name is Eric Sarmiento, and I'll be also the opening chair, as well as the chairman of the first session. Okay, as you know, this conference has an important and long-standing tradition in the complex fluids or soft matter community here in Mexico. Gathering each year for more than 30 years, postdocs, students, and local professors will invite professors, experts in hot topics in the area. Many of the current generation of faculty professors at the University of Mexico first had the opportunity to attend an international meeting as participants in this conference. This meeting started more than 30 years ago at the University of San Luis Potosí by the Professor Magdaleno Medina, who organized the complex fluids meeting for more than 25 years. The conference then was moved to Puebla, very close to Mexico City, for a couple of years, returned to San Luis Potosí, now handled by a new generation of organizing. And now the University of Guanajuato is the main organizing institution of this conference for the second year in a row. To all previous organizers, thanks for your effort that gave us one of the most representative and important meetings in physics topics in Mexico. Before anything else, let me introduce the organizing committee that you should be seeing this moment. Please, the organizing committee, if you can open your camera briefly. From the University of San Luis Potosí is Iván Guerrero and Edilio Lázaro. From the University of Michoacán, Gabriel Espinosa. From the University of Hidalgo, Víctor Trejos. From the University of Guanajuato, Susana Figueroa, José Antonio Reyes, Julio Almas, Francisco Alarcón, and myself. We all thank your interest in this conference, hoping to have a very productive one. Thank you. This year's conference is the second time the conference is held virtually, and even though we're really looking forward that this is the last time it takes place this way, so we can meet again personally. This gave us the opportunity to gather a high number of invited speakers from countries such as United States, the Netherlands, Japan, France, Chile, and Argentina. This year we will have 15 invited speakers, 11 contributed talks, and 32 posters. So to start this opening ceremony, let me introduce the director of the Science and Engineering Faculty of the University of Guanajuato, who will be opening the conference. Professor David Lepin, could you please give us the honors?
Thanks a lot, Eric. So first of all, thanks a lot to the organizer to choose for the second time Guanajuato and Leon and our division as the seed of the conference. So it's the name of the General Rector, Dr. Luis Felipe Guerrero Gripino, and the Rector of Campus Leon, Dr. Carlos Hidalgo Valadez. I'm welcoming you in Guanajuato University, and especially in our Division of Science and Engineering. So it's a great pleasure for me to receive you the second time, even still virtually, but I hope that soon we will be able to do it in a hybrid scheme or to see you here in Leon. So I just want to remember you that all of you, all participants, organizers, have an open invitation to visit us at in our division. So please just contact Eric, contact Julio, Susana, José Antonio, Francisco, and all members, and it will be a pleasure to receive you in our division. So I will not take more time because I think that you have a lot of important talk to hear. So let's to declare open the 33rd International Conference on Science and Technology and Complex Fluids here in Leon, Guanajuato, from the 25th to the 28th of October. Thanks a lot for all to be here with us. Thanks a lot.
Thank you so much, David. Okay, so before anything else, let me change the view to gallery. Thank you, thank you. So before anything else, let me do a couple of announcements. For the attendees, you can ask anytime using the Q&A button in the Zoom interface. The question will be directed to the speakers through the chair or answered directly by the speaker. If you want to ask the question directly to the speaker, please raise your hand and we can open the microphone for you so we can have a better interaction. For the poster presenters, please note that the poster should be posted in the Twitter account as soon as possible today. And please be sure to answer any direct message or request to meet by the other attendees. So let's start with the first invited talk. We have Anina Salonen. Anina, are you there? Okay, yeah. So Anina is from the Laboratoire de Physique de Soli, Université Paris-Saclay, France, and she will be delivered the talk entitled, I'm so sorry because I'm looking for the title, Forms with Viscoelastic Continuous Phases, Changing Foam Coarsening with an Emulsion. Anina, thank you so much for accepting our invitation.
So, thank you very much. Oh, you can see it now, I hope. Sorry, I'm just arranging so that I see a little bit of someone so that in the view. Okay, perfect. So thank you so much for the invitation. So I'm Anina Salonen and I'm really delighted to be talking to you about our work. Although, of course, I'm hoping to see you all in person at some later stage. So I'll be talking to you about our work on foams with viscoelastic continuous phases. And so to start immediately on the topic, so this work was carried, so to just introduce in our group in soft matter at interfaces. So here you see a photo a few years back, and so I'll be showing the pictures of those who were really doing the experiments in this, but this gives you, some of you will see some friendly faces that you might have known before. So so this is our group, and so what I'm going to be talking about is foams with complex fluid phases. And so to start thinking about foams first, so here I'll just show you kind of some examples of foams, foamy materials. So you can see, so I'll just change this. So what we can see is you can, of course, use it for cleaning, shaving foam in drinks, chocolate mousse or whipped cream, or then going towards solid materials, so solid foods. So in all these different cases, they're all foams, so they're all bubbles in a fluid or a solid, but they have very different properties, they're very different uses. And so the questions I ask is basically, how can we control the foam properties? How can we control the stability of these different types of foams? So just to make sure that we all agree on what are foams. So of course, foams are gas bubbles in a matrix. So here you see image of a foam. So you see the kind of typical, so what's clear is the gas bubbles, and then in between you see a network of channels that are liquid and liquid foams, and of course solid and solid foams. So when we talk about foams, we want to characterize foam properties. They depend very strongly on the bubble size. So of course, an individual bubble, we can have the size RB, but in general, we have a collection of bubbles. And here you see a collection of bubbles which have a certain polydispersity. So we'll be thinking about the average bubble size that when I talk about R, I don't put always the brackets around, but it's basically, it's an average bubble size in my system. So to characterize my foams, the bubble size is important, but another parameter that's very important, it's the liquid fraction. So this is basically how much gas and how much of the liquid do I have in it. So if the liquid fraction is 0, I have just air. And if the liquid fraction is 100, I have just water. So basically, starting from either side, so we start with pure air and we start adding a little bit of liquid, we see something with these very straight films, straight films or straight plateau borders around the bubbles. And so this is something like, as in the photo here, this foam has around, it has a few % of liquid in it. So this is kind of typically what such foam looks like. As we start increasing the amount of liquid in our foam, basically what happens is our channels, the foam channels, the plateau borders will grow thicker and thicker until the jamming transition. So if we have a disordered system, this around 36%, of course, at this point, we no longer have films, we'll just have a collection of spherical bubbles, which if we dilute further with more liquid, we'll have a bubbly liquid of separate bubbles. So what I'll be talking about different systems a little bit kind of across the range of liquid fractions. So this is a little bit about the foam structures. And so then why, what kind of foam properties are we going to be thinking about today? So of course, foam, you take a liquid and air, liquid and a gas, and we get a solid. So here's just a photo of some shaving foam, so we can clearly sculpt it. So it has in general foams, we have a short, a linear elastic region. So what we're going to be thinking about again today is mainly the elasticity of the foams. So as we shear them, they'll be elastic for a certain while before they start yielding and flowing. So this is of course one of their mechanical properties is one of the reasons that foams are so popular and so widely used, is because you can have these very different, so because the texture depends a lot on the shear, so basically you can have these flow curves. So not flow curves, basically as you shear, you go from this elastic material to a flowing material. So another thing about foams is, of course, if you leave them for a while, they will age. So all these liquid foams, they will destabilize. So you might start from something that's very homogeneous with a lot of small bubbles, but if you wait a sufficiently long time, you will get a distribution of bubble sizes. So here you see a foam that has been aging under gravity. So what you see is that what we don't see much at the bottom, we have the liquid that has drained through the foam. So the liquid has gone down and the bubbles have gone up. And so you tend to have in equilibrium, you have a wetter foam at the bottom and this very dry foam at the top. So the foams destabilize through three different aging mechanisms. There is drainage, so gravitational drainage because of the density difference, and then we have coarsening, so coarsening as the gas transfers from smaller bubbles to bigger ones, and then coalescence. So today I'll talk to you a little bit about the elastic properties of foams and then their coarsening. So these are kind of general about foams, but in particular what I'm interested in is what happens when the continuous phase is viscoelastic. So unlike something which might be a slightly non-Newtonian, or if we take very dilute soap solutions, basically their rheology is like that of water, so they're Newtonian fluids. So what I want to see is what happens if we now change the continuous fluid. And we're going to start making a continuous fluid that is basically viscoelastic. So why would you want to do that? I mean, for example, I've highlighted here in yellow the systems where the continuous phase is viscoelastic, elastic or solid at some point. So you have whipped creams, you have chocolate mousse, this is some bitumen with bubbles in it, or then this kind of natural polymer spit solution of the insects. And then, of course, any solid foams, in fact, the solid foams during generation, in order to get the bubbles in, they're in general made from a fluid precursor, which then solidifies in time. So you go through, they're starting from a less solid material going to really an elastic solid. So that's why understanding what happens to foams from viscoelastic materials, it's also important because a lot of our everyday foams are such systems. So we can think about our kind of viscoelastic foams a little bit more. So what you see now is on the left we have liquid foams. So what I call liquid foams is the photo I saw. This is if you take some washing up liquid, you put bubbles into it. We have very nice, nice material. And so in these liquid foams, their stability, so how they age, is largely controlled. The kind of medium-term stability is really controlled by the mechanics of the interfaces. So basically, if they resist more or less to deformation, to flows, is when the systems are more stable. And same thing, the rheology, when I say surface mechanics, it's basically how easy it is to deform the interface of the bubble. Then on the other side, we have solid foams. So of course, a solid foam, by definition, it's not going to age very much. And then it's going to, the rheology, it's mainly controlled by the mechanical properties of the bulk material. So if we have foamed cement, it will be the properties of the cement that's in between the bubbles. And of course, what matters also is how much is there of it. So in between is what we have these foams from complex fluids. So for me, these are systems where basically both the stability, in their stability, both are important. Both are important, what happens to the surfaces and the bulk, and what's important is to the mechanical properties is basically deformation of the bubbles, but also deformations, for example, to the continuous phase. So these are the kind of systems that we want to be thinking about today. So I'll talk about two things. I said one about mechanical properties of these bubbly systems, and then I'll talk a little bit about the aging process. So here, the coarsening, this is the elasticity of our system. So we're looking at the elastic modulus. So this is work that was done by Maxime Schneider during his PhD, and working with Sandrine Mariot for all the confocal images, and with Olivier Pitois from Marne-la-Vallée, IFSTAR, with whom we're thinking about the understanding basically what's going on. So we're going to be now putting bubbles into an emulsion, and we'll start looking at the properties. Up. So the system we're going to be using as our viscoelastic phase, it's going to be an emulsion. So basically all through the systems I'll talk about today will be, schematically something like this. So you'll have these white air bubbles surrounded in a blue water and with yellow oil droplets. So in each case, we have a system like this. So depending, so here you see a close-up. The scale bar is not showing. So these bubbles are around 100 microns. And so what you see is basically these air bubbles. So this is a photo taken under the microscope. So you see through the bubbles, and you see this sea of smaller oil droplets. So these are rapeseed oil drops around them. And so what you see is a kind of decoration close to the surface also of the bubbles. So you see, what you see here very finely is basically due to the curvature of the bubble, you see a thinner layer of oil drops. So you can really distinguish them very finely here. And so here is a photo of a bubbly, really a foam. So here we have a lot of gas and the emulsion in between, whereas of course we can also play what I said with the liquid fraction, so the amount of emulsion in our system. So here we just have some bubbles in an emulsion. So we're going to be thinking a little bit about their mechanical properties. So if we think about the linear elasticity first, just of foam, so first we want to think about how easy, so basically now to start, I said we're going to look about the rheology of foams from complex fluids, but we get started with a little bit just reminding ourselves, or I'll tell you a little bit about just foams. So basically, if I want to shear bubbles, basically how easy it is to deform them depends on the Laplace pressure. It's proportional to gamma over r, where gamma is the surface tension and r, it's the average bubble radius. So this is kind of tells us how easy it is. So the elastic modulus of our system is proportional to gamma over r. But in fact, more specifically, it can be written. So this is the expression. It depends on the liquid fraction in it, and so this gamma over R with alpha a constant. So this is the elastic modulus of a foam. So here I plotted as we increase the elastic modulus, the liquid fraction decreases. So here these actual real values. What I forgot to say is I took a typical surface tension of soap solution, and this is actually with huge bubbles. So this is with a 1 millimeter bubbles. So if we go to 100 micron bubbles, so we have a factor 10, we immediately have go to elastic moduli rather between 100 and 200 Pascal. And so you see that as the liquid fraction increases, the amount of the elastic modulus of the system increases, because basically there's less film between the bubbles, so the modulus decreases. And so another way that we can change the elastic modulus is, of course, in time. So if our foam is coarsening, so as the bubbles go from smaller to bigger, R goes from smaller to bigger, and so then we have an elastic modulus that will decrease in time. So here basically we start with bubbles that were a bit below 100 microns, and then they coarsen, they grow in time, so the elastic modulus decreases. So now we're going to put in some emulsion drops. So our emulsion drops, I mean, basically it's the same idea. We have drops that are going to be deformed. Typically our oil drops are smaller. So you also have so this is in units of gamma over R. So you also have if you normalize with the surface tension and radius, you see that things are together. So this from the literature. You have basically again, a weak hits in a log scale, but you have some variation with the volume fraction of drops. But here, what I want to say, and what's important for the rest, is basically what you see is with the foams. If we have repulsive bubbles, typically there's no elastic modulus below random close packing, but you can get an elastic modulus in random close packing if we have attractive interactions with the emulsions. So the emulsion is a nice system for us for the continuous phase, because basically we can vary the elastic modulus with the changing oil volume fraction and drop size. Okay, so now if we start looking at, if we want to compare a little bit the contributions of the emulsion and the foam, we can define what's called an elastic capillary number, which is basically what I call G0. It's the elastic modulus of the emulsion, so it's the G emulsion divided by gamma over R, which is basically proportional to the elastic modulus of our foam. So what this means is that when at very small elastic capillary numbers, we're basically completely dominated by the deformability of our bubbles. And when we go to very high elastic capillary numbers, we're completely dominated by the elastic continuous phase. So we have another parameter, which is of course the gas volume fraction. So we can also think about, so I talked about whether we have wetter or drier foams, and this allows me to show some of the work that has been published. So people have looked at a lot either single bubbles, so the work of Robert Style or Duclouet, where they were putting so in Robert Style, it's individual bubbles in an elastic matrix, or then Duclouet, she was starting to add more and more bubbles, and then Gourlier, they kind of put the normalized elastic modulus, so elastic modulus normalized by the elastic modulus of the continuous phase as a function of the volume fraction. So what we want to do is to start looking at really small elastic capillary numbers. To see, so that's what we're going to first look at, to really try and see the so small elastic capillary numbers where the limit between foams and elastic materials. So how do we do it? What's our system? We're going to make an emulsion from rapeseed oil and 30 grams per liter of SDS, sodium dodecyl sulfate. So it's a charged surfactant. We just put a lot in to basically stabilize our emulsion. So we make the emulsion with 2 syringes. You fill one part with oil, the other part with water. Your surfactant solution, we go back and forth, and we make drops that are a few microns. Then we refill the syringe with some air, and we're going to do is now start from an emulsion and air, and we go back and forth several times, typically 20 or 30 times, and then we get gas bubbles in a continuous sea of emulsion droplets. So that's how we make our foams. And so what we end up with is basically weakly elastic emulsions. So we have, if we do then, we look at the linear elastic modulus. So if we look at the elastic modulus as a function of the strain, so here we have the G0 of our, here I'll show you with 3 different emulsions with 50% oil, 60% oil, and 70% of oil. So in each of the cases, the drop size is around 2.5 microns, and the bubbles we make, there's basically a factor 10, they're basically a factor 10 bigger. And so these are really small for the 50, it's really small, but values were at a few Pascal for the lowest emulsion concentration. So then we get, can vary the elastic capillary number from 10 to the -3 to 2 10 to the -2. So what do we expect? Sorry, what do we get first, then what could we expect? So the elastic modulus of bubbly emulsions, sorry, it's a bit blurred here. So what you see is, for example, for each one, the one in the full color is the emulsion, and what you see is an increase of the, so then as we add more and more bubbles, we go to lighter and lighter colors with it. So what you see typically is that as we increase the volume fraction of gas, we increase the elastic modulus of our emulsion. And what you can also see is that basically the lower the increase is stronger, the smaller the initial elastic modulus. So basically we get the change of elastic modulus in the presence of bubbles. So what can we expect? So just very briefly to say what we could expect. So if we think about our blue, now just schematically, our blue elastic continuous matrix with our inclusions, which are now in green, with the G0, the elasticity of the matrix, and phi, the volume fraction of inclusions. If the inclusions are solid, we can use basically the Creek-Doherty description, which was first made for linear viscosity, but in fact, it works also for the linear elasticity. So this is the description. So what you expect is in blue, sorry, it's completely inverted, of course. No, it's fine. Blue is no slip. So basically this means that the boundary, we have a 0 velocity, and there is no slip between as the continuous phase flows, there's the contact between the particles and the fluid. And then in green, if we have slip, so basically if there's a slip boundary condition, we change the strengthening with solid particles is smaller. And then what you see in the black line is you can also, there's basically micromechanical calculations to show that if you put holes in it, so now it's really just making a hole into a elastic matrix, we get this weakening effect. So we can imagine that our bubbles will have something in between. And in fact, we shouldn't reach the solid particle behavior. And so what do we see? So we're going to again use this normalized units. So this G prime now is the elastic modulus of our foamed bubbly emulsion, and G0, it's that of the emulsion. So I replot some data from Duclouet et al. That I showed you in the first figure. So basically what they did is that they showed that you can have a description now taking into account the elastic capillary number. So as I said before, you kind of imagine that we start, this is kind of the most weakening case as you put holes in, because there's no resistance to the holes. So as the bubble size decreases, elastic capillary number increases, decreases, you go towards a more a stiffening by the bubbles. And so this is what they proposed in their soft pattern. So this works nicely for the red and the blue results that we had with the 60 and 70% emulsion continuous phase. So if we add So here we really show for the first time a strong stiffening of the emulsion by the addition of the bubbles, and we can describe the data nicely using the model proposed by Duclouet and her colleagues. So now you can maybe see that there's one series missing. So if I add my final series, in fact, it's much higher. So here we're now beyond, in fact, already with the small elastic capillary number in red is what these what we'd expect from the model of Duclouet. So what we see is if we put in really assuming that they're solid particles, I mean, we can only have no slip on the bubble surface with the emulsions. So we really have we're even slightly above this. So what we're saying is that the bubbles really increase, the small bubbles at small elastic capillary numbers, they increase the elasticity of our emulsions more than they should. And so this is actually linked, if we remember this image of confocal microscope. So this is our emulsion, and so the emulsion at 50%, it's not above random close packing. So we have more like something like a gel, and so this gel can in fact be a little bit reorganized, and our bubbles can participate really participate in the network of the gel. And so here, what we then looked at, so this is what we're saying is that the particles, our bubbles, will participate in this gel. And so what we then looked at is if we change a little bit the inclusion size. So this is now changing the inclusions. So we have tiny ones going to bigger ones and then huge inclusions. So sigma, it's our ratio of the size of inclusion to size of the emulsion. You see a very strong effect. And so this kind of gave us the first hints that there's really an interplay between the bubbles and the emulsion matrix, also at these, because the bubbles are reasonably small. And so here, I'm not going to go more into it, but if you want to know more about the origin of the stiffening, you can go and see Claudia, who has a poster with simulations and experiments, now with solid inclusions in a gel matrix, and she will be able to tell you really on a microscopic view what's going on. So I'm just going to conclude on what I've shown you with the bubbles, is that we can reinforce emulsions if the elastic capillary number is very small. The emulsion elasticity is increased as the bubbles, they modify and participate in the drop network. And this means that we can make elastic materials with lower emulsion volume fractions, but really comparable mechanical properties, which is very interesting. So if you're interested in trying to use the continuous phase, viscoelastic continuous phase to change the properties of foams, you can also look at what we did very recently on looking at colloidal gel, which develops inside the foam channels and also stiffens our foam beyond what we'd expect. So I hope I still have some time for my second part of my talk, which is, as I said, I want to tell you a little bit about the mechanical properties and then a little bit about the aging. So the question is, how is the aging of the foam changed now by the presence of the viscoelastic continuous phase? So after I'm just looking at the time, I think it's okay. You let me know if I'm running over. So what? So we're going back to the idea of now looking at the destabilization. So I told you that the foam's destabilized by drainage, coarsening, and coalescence. And in fact, we're in particular looking now at the coarsening. So we're looking at the coarsening because, in fact, what I don't show you, but the gravitational, basically the gravitational stresses are reasonably small. And as long as we have a yield stress of some Pascal, we can stop the bubbles from creaming for quite a while, the bubbles from creaming and the liquid from draining through for quite a while, until they're very big. But so what we're going to be really thinking about is as the coarsening. So this work was done by Chiara Guidolin. So here's Chiara making some using a little cappuccino mixer to make some foam in an emulsion in the lab. So Chiara's finishing her PhD at the LPS with myself and my colleague Emmanuel Rio. And this project we've been collaborating with Jonna McIntyre and Antti Puisto from Aalto University. So we think about coarsening. So here to show you a video of coarsening. So coarsening, it's basically driven, so bubbles coarsen, they age because of Laplace pressure differences. So the pressure inside bubble I, which is smaller than bubble J, so as the bubble is smaller, the curvature is higher, and hence the pressure is higher. So we have a driving force. Laplace pressure is the driving force for the gas to go from the smaller to the bigger bubbles. And so here what you see is in fact why it looks so sharp. It's really a video you're looking at. I mean, it's been inverted and image treated, but it's really a video of coarsening. So what you see here is what we call the quasi 2D, hence in the title quasi 2D. So we have a single layer. Quasi 2D means we have a single layer of bubbles between two plates. So if you look from the side, it looks something like this. So all the bubbles are squeezed, the bubbles are bigger than the gap. And then you have in between, you have our liquid, which will be the emulsion. So this video is made with a fairy liquid, which is in fact, so it's a washing up liquid, which is used a lot because it makes very stable foams against coalescence. So it's basically a washing up liquid to make a kind of a normal aging foam. So if you look at the video here, so here, for example, you can see this little bubble that's being eaten up and it disappears. And if you look at, I think the video is going to start again soon, but if you look at this one, again, you see the small ones are driven into the big ones. So this is basically as the foam coarsens, the bubbles, some increase and some shrink during the process. But then you also see there's kind of some dynamics. So we have, it's called the T1. So it's a topological one when we have really a change. Where do we have as bubbles? So it's not when the bubbles disappear, but as they relax stresses and they rearrange their neighbors, we see some rearrangements. So it's kind of a pretty dynamic system. And so this is what happens in a normal foam. So of course, people have looked at the coarsening, and there's the models for the coarsening of aqueous foams exist. So this is the volume, so to the power 2/3 as a function of time, the volume of the bubbles coarsening. So we get a straight line because it's a dry foam, and basically this is what we'd expect. Power to the 1/2 for the radius varies as t to the power 1/2 in dry foam coarsening. So what do we in dry foam coarsening? It's basically diffusion limited, so the gas is going through the films, and we also assume that we're in a self-similar growth regime. So these are basically different. So this is again in 2 dimensions simulation. So you see in different times of the process, it's self-similar because each time if you zoom out. If you zoom in to the first one, it would look the same. So basically the bubble distribution is invariant. And then what we have is b to the beta, the exponent in the Ostwald ripening limit, in the wet limit, it would be 1/3. So this is what we know for aqueous, dry and wet foams. So again, the same question, what happens when I put the continuous phase change a continuous phase into something viscoelastic? So of course, we're not the first ones to think about it. So here again, here you see a few references. So from Klock and collaborators, Webster and Cates and Bay and co-workers, what in particular Klock and Bay were looking at is to kind of see the limit. If your continuous phase is sufficiently elastic, you stop coarsening. So you have a prediction. So if you're basically in a foam, it's not quite, it's almost if the Laplace pressure, if the yield stress of your foam is higher than the Laplace pressure, it's not going to be able to coarsen. So what we want to see is, again, we're kind of in between in the limits of slightly, not really going to this stopping limit of when I'd say we're going to a solid foam, but being a bit below, so having systems that still evolve. So how do they evolve? If now we basically restrict a little bit the movement, so the dynamics in our foam is changing because they can't rearrange so easily. So what happens? So the system, it's I think you've seen I like foamed emulsions, so it's the same system. So we have, so this again, in fact, the photo from before. So we have the air bubbles, we have the droplets around, and so in this case we start with bubbles that are a little bit bigger. So we now make them with differently. So we have a radius around 100 micrometers, and the oil fraction, it's now with very high oil volume fractions. So really going to, we're kind of factors of last time we were looking at a really a few Pascal up to max a 10, because we're around up to 70% of oil. Now we're really going to the higher volume fractions of oil, so going to higher elastic moduli. Oops. I think you see my colleague going through. So here we have so we're going to really higher elastic moduli with these high concentrations of emulsions. And so again, the bubble size, drop size is around 2 microns. So the drops are always much smaller than the bubbles. So how do we make these? So we make them a little bit differently. So the emulsion is again the same. We make it with 2 syringes going through mixing with 2 syringes to get our emulsion. But now the thick kind of 85, it's really pasty emulsions. You can't mix them with the 2 syringes. It doesn't work very well. You can't incorporate much air into them. So what we do is we use a kitchen mixer. So Politova and her co-workers, they looked at how it works a bit, but basically it's really a Kenwood, and you see it's not advertising the mark, but it's really a planetary mixer with a whisk that's whisking around, which then pulls in air pockets which are sheared to make this foam. So we start with a 3D foam. So then we put it into between 2 plates. So saying we're quasi 2D foams. So we have a 1 millimeter, it's a pretty small gap. But initially our bubbles are 100 microns. So we start with a 3D foam, and then we wait until it gets 2D, and then we start observing it. So I'll show you in the next image is what we see as we take a video. So these are 70%, 75% and 80% of oil. So these videos. The real total time, it's around a week. And here they're quite dry foams with about 10% of liquid fraction. So you can look at them if we start with a 70%. So again, it starts in the beginning soon. So this 70%, it looks a bit like a normal foam. It's again moving, rearranging, coarsening. And if you really can detail, it's a little bit strange, but nothing compared to the other ones. So here you start to see some kind of slightly funny shaped bubbles. And in fact, if you now look at the final, the highest concentration, the 80% here, you see that here, for example, you're really retracting slowly this emulsion around, and you start seeing these super thin, long straight plateau borders and these regions of foam. Smaller bubbles, so there's clearly things are changing. We have funny shapes and non-equilibrium foam structures. So the question is, what's going on? So we do, as people have done for the normal foams, we start characterizing these images, and we say, okay, let's measure the average radius. Where's my pointer? So the average radius as a function of time. So my pointer's not moving very nicely. So what you see here on the y-axis is the radius. Now it's been normalized by the time at which it becomes 2D as a function of time. And in fact, in the inset on this image, no, my pointer doesn't want to go there. In the inset, you see the number of bubbles as a function of time. And so here you see that we really have a lot of bubbles. We're at 1,000 up to 10,000 bubbles in our system. So what we can see is that I've drawn a 1/3 line, but our foam's dry. It should be a normal, if at this liquid fraction, a normal foam would be closer to a half. So we see that the coarsening rate's slower than what we'd expect from diffusion limited growth, even for the 65 sample, which is the palest red one. And then we see that the coarsening slows down with the oil volume fraction phi, so the elasticity of our foam, of our emulsion. So we have the radius, and that's evolving here. So then what we wanted to see is, I told you about the rearrangement. So basically, if we look at the number of rearrangement events, and so we can look at here briefly the number of rearrangement events as a function of radius of the foam, average radius of the foam in time. And so what you see is that for a given radius, the more elastic our system is, the darker the color of the points, so the less it moves. So even if, so what this means is that, of course, for a kind of a normal foam, what you'd expect, what we know is that because things are self-similar at any given, if the radius, average radius is the same, then it would be the number of rearrangements should be comparable. So here basically it means that it's not the bubble size that will govern the dynamics in our system completely. The elasticity of the continuous phase also plays a role. And in fact, you saw previously that the coarsening rate is slower. And so if we look, we can now define the dr dt. So this is the slope of the coarsening rate. And so this, in fact, this is also slower as the elastic modulus is higher, and so the number of T1s actually scales as the rate of coarsening. So this means that we can't distinguish whether it's the coarsening rate that's slower that then has less T1s, or whether we have less T1s that has a slower coarsening rate. But so we start looking at now. We look a little bit at the distributions to see how well. So clearly, from this figure as well, and the coarsening laws, we don't expect to be in the self-similar regimes of kind of normal coarsening. So what are the bubble size distributions look like? So here I show you the bubble size distribution. So we have 65, 75, and 85 volume fraction of oil, and so this is the normalized radius, and so this is the probability distribution of the radii. And so what we have is in time, so the lighter colors are early times and darker colors are longer times. And so you can see that the darker ones are all very different, and I should have added maybe initially they're actually all very similar. So the pale ones initially, they all have very similar shapes. But what you see is that the higher the volume fraction of oil, the weirder and weirder looking the distribution looks like. So we're basically going to a more and more skewed distribution. They become more asymmetric, and the higher the volume fraction of oil, the more asymmetric they come. And in fact, how do they become asymmetric? Is that what we see is that, in fact, we're kind of shifting. We have this peak of small bubbles, and this is actually, we're struggling to, we have a lot of small bubbles in our system. So in fact, we're shifting the distributions. We have too many little bubbles in our system. And so why do we have small bubbles? Why are the small bubbles left behind? They don't disappear fast enough, but why is this? So if I have time, hopefully in a few minutes, I'll tell you why we think they don't disappear fast enough. So to think about why they disappear so slowly, we now start thinking about, we think it's for two reasons. One, it's that around small bubbles, there's more emulsion around them. The liquid fraction locally is higher around a small bubble. So if I look at the, it's not exactly the local liquid fraction, it's proportional to the local liquid fraction. It's a parameter we use as a function of the radius. The smaller the radius, the more liquid you have around. So the foam is wetter around small bubbles. So this doesn't really help us, because if we look at normal foams, if you remember, we have the elastic modulus, which goes down as the liquid fraction increases. So the smaller bubbles would be freer to move than the bigger ones. So, but we have our emulsion around. And so this is the figure I already showed you. We can have this change of slope. So basically, the wet foam, we have a liquid fraction that goes down. As the liquid fraction increases, the foam is less elastic. And sorry, here it's 1 minus epsilon. So basically what we see is that if with the elastic upper number is high, we have an inversion. So basically what you see, and this curve can have a changing slope. So at high, at very dry foams, you can basically have a region where it decreases as the foam gets more, has more liquid in it when you're still dominated by the bubbles, and then it goes up as we have a higher, more dominated by the continuous phase. So basically what we think is that the bubbles now, they experience a different surroundings, and so in fact the small bubbles get stuck because around them it's more elastic. So we can estimate that for our foams. So if we estimate the elastic modulus, so now again 1 minus epsilon, so these are at a radius, we fix a radius of 1 millimeter. So that's when they become 1D. What you see is for 65, the slope, we always have a positive slope. So this means that if it gets wetter, it's less elastic, it can coarsen, whereas for the 85, we have this inversion of slope. So we start at 10%. So the wetter it gets, the more elastic it gets. And so we think this is what's hindering the coarsening at some point. And so what we can do is now, if we fix the elastic modulus, we can see, okay, they're coarsening, the bubble size gets bigger. So at what bubble size do we expect the elastic modulus to start to change the slope? So we could expect that if we have an increased elastic modulus around the smallest bubbles, this is when our behavior should change. So to compare this to experiments, to compare this, I'm going to get the time again, so do stop me. I think I'm done in a few minutes. So if we departure basically from normal foams, so how do we define it? It's basically when we start having these small bubbles that are getting stuck. So we're going to get a measure of it by measuring the skew of the distribution. So if we plot the skew, so the mu3 of the distribution as a function of the radius, so what you see is that the smaller the oil fraction, the later is the departure of the kind of the start of the skew. So we're just going to define, just to get a comparison, R star experimental as the radius at which the skew becomes above a certain threshold value beyond the aqueous foam sizes. So then we can do this, and it works pretty nicely. So we can plot our kind of experimental value as a function of the estimated value from the rheology, and we get a linear dependence between them. So that's pretty nice. So we think that it's really linked to the bubbles, the bubbles slowing down, which gives us these funny phenomena. So the slowing down of coarsening, it's basically linked to the smallest bubbles evolving in a more elastic matrix. And so this brings me to my conclusions. And so what we've shown in the second part is that the viscoelasticity of the emulsion, it slows down the disappearance of the smallest bubbles, which leads to slower coarsening and uncommon bubble size distributions and foam structures. And so in fact, if we take a final look now really of the structures, you see that these structures are very special. So I didn't really talk much about these structures, but just to finish, I'll just show that they do remind us much of the viscoelastic phase separation of a polymer system. So this is a photo from a paper by Tanaka. And so we think that here, the phase separation process is really very similar to that seen in polymer mixtures because of this dynamic asymmetry, so between the two phases that are coarsening. So that brings me to my conclusions. So I've been walking around a little bit, looking at the aging and rheology of on our diagram of elastic capillarity and gas volume fraction with our coarsening and our emulsion experiments. And so here I just leave the conclusions of the two parts to say that the emulsion elastic modulus can be strongly enhanced and the coarsening can be really dramatically changed. And I think both of these are important in the design of soft aerated materials, which can be in food, cosmetics, and construction. And then I'll just put to the thank you to those who've been financing this work, and I thank you very much for your attention.
Thank you so much, Anina. Thank you for this very nice talk. So we now move to the question. Does anyone have a question for Anina? Yeah, we have Gabriel.
I stopped sharing to see.
Okay. Can you hear me? Hi.
Yeah.
Hi, Anina. Thank you very much for your very interesting talk, and thank you for accepting this invitation. And I just have a very quick question. I remember talking with Dominic. She said that stability or stabilization of the emulsions, foams, are mainly or is very dependent on the time, the relaxation time, the characteristic relaxation time of your viscoelastic liquid. Did you explore this on your experiments, or is just like you understand everything on the relaxation time and you just focus on the elastic modulus?
No. So basically, that's a very good question. But basically, you're completely right. So basically, it does. I completely agree with you. The relaxation times are important, and I think where we're going is we're kind of going towards the continuous phase relaxation times being longer than the relaxation time. Basically, the typical diffusion time scale to coarsen, which is what plays a role. And so I think we're in the limit where the diffusion time scale is now slower than the rearrangement of the emulsion around, and then this allows us to have these different structures, which I think then are also controlled by the other properties, the elasticity, but also the yield of the emulsions.
I see. Okay, it's interesting. Thank you.
Okay, anyone else? I have one question. Well, it's more like a comment. As I can see, this difference on the pressure between big and small bubbles is the reason that in normal conditions, the small bubbles disappears faster than the big one, right? Mm-hmm. And then you found a mechanism that is giving, let's say, more time for the small bubbles to stay in the foam, right? Mm-hmm. And then what is very interesting is that the distribution that you have it reminds me some the distribution of the free area, for example, in two-dimensional colloids. I mean, if you have a normal two-dimensional particles moving Brownian, and you for example compute the Voronoi area, distribution area, is more similar than the new case, where actually you can have small free space. In this case, smaller foams or balls than the other case. So that means that it's like more. Is not there is no reason for the small bubbles to disappear, and it's more like a random distribution of sizes. That is the origin of, for example, this Voronoi distribution that is quite similar to yours at the end of your talk. So that's as you indicate, this also it seems to be another very similar distribution for this difference when you have this viscoelastic medium. So it was nice to see it.
Thank you. No, that's
okay. So, any more questions from the attendees? Okay. It seems that we don't have any more questions. Thank you, Anina, again for your contribution.
No, thank you very much.
So our next speaker is Lynn Walker from the Carnegie Mellon University. Hi. Thank you for accepting our invitation, Lynn. So, and ready when you are, please.
Sorry, my controls move things around. I hope everyone can see my screen. If not, someone should yell.
It's okay.
Thank you, Eric. So thank you very much for the invitation. I was very excited to be invited to the meeting and certainly wish we could be in person, but I have known of this meeting for a long time and have been very glad to see it happening and glad to be involved. So thank you for the invitation. Since this is, I like to talk to meetings where we're targeting students because it gives me a chance to show off some of the area that I think is very important and very important to the future of soft materials research, as was the research of the talk before mine, which I had many questions, but I didn't want to take into my own time. So let me get started. What I'm going to talk about today is some of the work that we've been doing in my group to understand how, as engineers, we can control fluid interfaces to get at some of the things that our last speaker spoke about. Whoops, sorry. What I want to first stress is to remind everyone of the length scales that we are discussing when we think about interfaces. At the nanometer length scale, we're looking at surfactants. We know a lot about how surfactant architecture, how surfactant structure, how the chemistry of a surfactant will impact how it goes to an interface and how it packs at an interface. We understand how things like to associate in solution, for example, polyelectrolytes and surfactants and colloidal particles. And so we have a pretty good understanding of what's happening down at the nanometer length scale. There's a lot of it of the world has been looked at this. At the next level up, we've got long history of understanding how these surfactants adsorb at interfaces and how that's converted to an interfacial tension or a surface tension. And there is some level of the ability to connect chemical structure to interfacial properties. You need to develop some sort of an equation of state. As we get into understanding interfacial mechanics, that's a little less understood, and I'll get into that as we move on. For these things, we're somewhere between the molecular length scales and now the length scales of a continuum interface, something in the micron length scale. And then finally, what we're interested in, as we learned from the last talk and many of you are working on, we're interested in macroscopic behavior, foamability and the stability of these foams, and then emulsification and the formation of emulsions and control of those. And so this length scales are up at the macroscopic end of things, microns to millimeters. And so we cover a wide range of length scales. And what we want to be able to do is control those fluid interfaces with processing, not just the chemistry. Why do we want to control these things? Well, I think this audience is particularly comfortable with thinking about these ideas, but we want to control interfaces because they control fluid phenomenon. For example, breakup of jets and drops, very important in new areas in 3D printing and in aerosol formation, which we've learned a lot about in the last 2 years. Those length scales are up in the millimeter range, but it is the interfacial properties that are controlling them. And over on the right, I have an image of some work we do in coalescence where we're interested in understanding coalescence time. And this is important for emulsion stability. Again, the interfacial properties dominate and control these things, as do the continuous phase fluid properties, but the interfaces are key, and we don't understand all of the fundamentals. We have a good understanding. There's been a lot of work over the last almost century, but we don't understand enough about the connections to engineer these things. Oh, sorry, I keep losing my mouse. So when I talk about processing of interfaces, there's two key things to keep in mind. One, the properties of a multi-phase material like a foam or an emulsion or a blend is defined by the fluid interfaces. All of the other properties of the fluids come in, but we do need to understand what the interfaces are doing. The composition and microstructure at the interfaces, where we have focused a lot of our time, is a function of the timescales of the system and of deformation of the interfaces and deformation of the system. In my world, that's flow or electric fields. Herein lies the problem. There's been a lot of work done on equilibrium or static interfaces. We've developed isotherms. We have done detailed static structural characterization through optical reflectometry, neutron scattering, light, X-ray scattering. We've really characterized the number of interfaces quite in detail. We can do detailed compositional measurements. So that side of things we have a pretty good understanding of. On the other side, dynamic interfaces, where things are moving and changing with time, as we've just learned, and we'll learn over and over again in working with these systems, we need to understand transport modeling to and from the interface. We need to understand formulation and compositional control, how mixtures of things and how competition between association in the bulk and association with the interface impact things. We need to understand interfacial rheology. These are all dynamic properties or properties of dynamic interfaces as I think of them. There is a huge gap here. There's a gap in our understanding. There's a gap in our ability to manipulate these. And I would argue there's a gap in tools to characterize the timescales and properties of the interfaces. And so that's where I've focused a lot of the last 10 years of my career working with collaborators, is to make use of microscale interfaces as a way to characterize this and fill this gap. We want to explain how to understand dynamic interfaces and how transport comes into a lot of these properties. So we're going to take advantage of a very old idea, which is the Laplace pressure concept. We've got good cameras and digital optics and things like that, and we can image things much more effectively and with cheaper equipment. So that came in, and then we have off-the-shelf pressure transducers that allow us to measure the range we want. So a number of things came together for my group and for a group of my colleagues about 10 to 15 years ago that let us sort of dive back into an old problem, and that's to take advantage of essentially a capillary pressure tensiometer. So we're going to capture an interface at the end of a capillary, and so that's what the image is here. This happens to be an air bubble in water, but we can do this with lots of other fluid interfaces. What you'll notice is there's a nice hemispherical cap. There's a nice hemispherical cap here that can be fit with a circle. And so if you think about the pressure jump across this interface, following the Laplace equation, the pressure jump is 2 times the interfacial tension divided by the radius. When the radius gets down into the tens of nanometers, tens of microns range, the interfacial tension, if it's a normal value of about 40, that'll give us a pressure jump of 2000 pascals. That's actually quite measurable with an off-the-shelf transducer. And so we're going to make use of a capillary pressure tensiometer. We're going to measure those pressure jumps. We're going to fit that radius, and that's where the optics and the new digital cameras that are around now come in. We can actually do this with your standard cell phone nowadays. So we'll put all these things together and we'll develop a tool that lets us look at transport to interfaces. And so we've developed a platform we call the microtensiometer platform. It's based on this idea of a capillary, which has one solution or air in it. You pin a interface at the end of that capillary. You can measure the pressure jump using a simple pressure transducer, and we buy a number of different off-the-shelf ones. You can measure dynamic interfacial tension because this pressure can be measured as a function of time as fast as electrons go. And the radius, which we're fitting a circle, we can do this on the fly at rates of a standard camera, 24 frames per second, or a high-speed camera if we wanted to. So the time resolution is now controlled mainly by the camera and fitting this circle, but routines that we have online can do this very rapidly. So we don't have to do it offline is the key. All right, so we can measure dynamic interfacial tension very effectively. We've done a lot of that. Nick Alvarez was the first student to build this up for us and do those measurements. We can also put a DC motor into the line and oscillate the pressure behind the capillary, and that will allow us to measure interfacial rheology, at least something that's very close to the dilatational modulus. So we're going to oscillate this interface back and forth, and we've corrected for things like curvature effect and stuff, but it gives us a very good measure of the dilatational modulus. And then finally, the reservoir that this little capillary sits in, because it's a micron scale interface, is itself only a few milliliters. And so we can exchange the fluid in the reservoir and change the bulk fluid properties suddenly near that interface, and then measure changes in interfacial properties due to bulk fluid exchange. We can also provide a flow if we want to look at the effects of flow. And so we've done a lot of that. And so we put all of these things together, and it lets us look at a number of different problems. And so I'm going to talk about two different systems that we've looked at today. And I might cut some little bits out of this, but I just want to get across the idea that multi-component adsorption is a very interesting area and one that gives us lots of knobs to turn as engineers. In my group, we've looked at mixtures of surfactants and proteins, surfactants and particles, and surfactants and polyelectrolytes. In all of these systems, the key idea to keep in mind is that these systems associate both in the bulk and with the interface. So everything in this system is surface active, everything is talking to everything else. And we need to keep track of that as we do our analysis. So the first thing I'll talk about is these polyelectrolyte surfactant aggregates. So these are a system that we've been working on for a while in my group. We polymerize the counterion in a wormy mice cell. That part of it isn't important. The result is, though, that we end up with a polyelectrolyte, and it's carboxylated polystyrene wrapped up on the inside of a mice cell. And these tend to be rod-like, 4 nanometers in diameter. That's very monodispersed because it's set by the tail length of the surfactant, and on average 100 nanometers long, but we do see some polydispersity there set by the molecular weight of the polymer. Things to note: the polymer, every single group on it is a charged carboxylate because we polymerize counterions. And then the surfactant is, in this case, CTAB, so cetyl trimethylammonium. And we've done a lot of work in looking at these rod-like systems. In water, they're very stable. The surfactant can dissociate from the aggregates, and we've measured the critical aggregation concentration. It's very low, and we're going to be staying above it for all of the work I talk about, but it's the surfactant that desorbs from these aggregates and then can interact with interfaces. We looked a long time ago at how these adsorb on solid liquid interfaces, and we see rod-like aggregates down on the solid liquid interface. So they maintain their structure as they adsorb. And so we wanted to investigate how this could be used to look at air-water interfaces. So we use the microtensiometer, and here's what our results tend to look like. Up here would be the clean air-water interfacial tension, 72 millinewtons per meter. We start with a bulk concentration of 0.24 mg per mil of these, what I call PCTVB, that's the aggregates. And at this point, they're roughly neutral, but the dissociation of the surfactant gives them a net negative charge. They adsorb very quickly. So we create a new interface, we blow a bubble, and the new bubble forms, and we can measure the dynamics very accurately. And we see a rapid drop in interfacial tension as the aggregates adsorb to the interface, and then it tends to flatten off. This block is where we're doing the oscillations to measure dilatation. So just so you know where it is. If I then exchange the reservoir for clean water, and so I remove the bulk material, but keep the interface the same, what I see is some rapid desorption, but it flattens off at a level below the clean interface value. So there's still some stuff stuck on the surface, most likely the big oily polymer molecule that I carried down there in the aggregates. Just to check that there's not something else going on, we blow that bubble off, and the new bubble gets right back to the interfacial tension of clean water because we've removed the bulk solution. So this is just our check that there isn't still something remaining in our reservoir that's trying to interact with the surface. What it means is that we can define two states based on the initial concentration. There's a steady state value for the interfacial tension, which is in equilibrium with a bulk concentration. And then there's the rinsed value, which is in equilibrium with clean water, or in steady state with clean water. But that is going to have been controlled by the previous adsorbed layer. So I can take a look at these two values as a function of anything I want to. And my student Michael did a large study where he looked at the effect of the initial bulk concentration of the aggregates. Here I'm reporting it just in terms of the concentration of surfactant, so I can compare things more easily, but this is really effectively the bulk aggregate concentration on the bottom. What you see if you look at the black circles is what we expect for polyelectrolyte surfactant aggregates adsorbing to an interface. This captures the CAC, the critical aggregation concentration. Below this value of 10 to the minus 4, we actually see the surfactant associating with the aggregates and the interface. And so there's a competition going beyond there. And then above a certain concentration, the aggregates are what are now absorbing at the air-water interface. Okay, and so we get this value that's nice and flat, and we don't worry about higher concentrations right now. If we then rinse the bulk material away, you get these blue circles. Now remember, each of these error bars captures 6 repeats of this. And when we do the rinsing, we've kind of lost the interface. So there's a lot of experiments in these blue symbols. What we see is that below the CAC, the material desorbs rather effectively, not quite up to the clean value. So there's still something stuck on the interfaces, something surface active, and that would be some fraction of the surfactant, but most of it is coming off. The surface pressure here is quite low. When we're above the CAC, we see different behavior. The rinsed interfaces go up in interfacial tension, which means that something is being removed from the interfaces, but it does not go back up to the clean value. And so what we're seeing here is a desorption, but an incomplete desorption of the material on the interface. And by the way, for all of these, we waited at least 1,000 seconds. And in some cases, Michael waited much longer to verify that these were reaching a stable value. Interestingly enough, if we measure the elasticity as measured by the dilatational modulus at these different interfaces, we find that that is high and is always the same. So values of 100 millinewton per meter are very elastic interfaces. When we still have surfactant in the bulk, we could be measuring just a transport phenomenon, but these light blue circles and the blue circles on the right are a system where there's nothing in the bulk. So we're measuring extra stresses of the interface. So what this is telling us is that when we rinse the interfaces, probably surfactant leaves, but the large polymer chains that were carried to the interface by the aggregates are unable to desorb. They're happier at the interface, and so they maintain a level of elasticity. And so these are now elastic interfaces with nothing in the bulk. And so we can control and make different kinds of interfacial properties. Just so you know, the open symbols on here are the comparison to just surfactant. Again, the CAC that we were measuring is consistent with what you see in mixed polymer surfactant adsorption systems. This high level tells you, this plateau tells us that it's mostly the surfactant controlling the interfacial tension, not the polymer. But the polymer controls the competition. And then the elasticity on the right is typical of what you'd expect for a surfactant system, and that's mainly measuring transport. So what we take from this experiment is the fact that the surfactant takes us down to the interface, it desorbs, but the polyelectrolyte is most likely remaining at the interface with some small amount of surfactant, and that's providing for us elastic interfaces. And we could only have learned this with those two types of experiments. One thing that we find very interesting is that these interfaces are processable, and this actually helps us back up sort of this assumption of what's going on. Here again, I show you our adsorption to the interface and then our desorption when we rinse the interface. We then add surfactant back into solution. Now, not the polymer electrolyte complexes, but just the surfactant. And we see that it goes right back down to this value here, which would be indicative of this being equilibrium adsorption of the surfactant. So the polyelectrolyte that was remaining on the interface becomes a sink. The surfactant adsorbs as if it, it was just a place for it to stick. And you can do this rinse and repeat in the shampoo world over and over again. So you can rinse these interfaces, put more surfactant on, rinse them, put more surfactant on. And in each case, it never completely comes off. And so that tells us that the polyelectrolyte is most likely staying on the interfaces throughout these cycles. It's a very persistent molecule at these interfaces. It's not surprising. It's a large hydrophobic polymer. It wants to be at this interface if we can get it there. And in all of these cases, the elasticity stays about the same. So the elasticity really comes from this polyelectrolyte that we've abandoned on the interface. This is just to indicate that, if we had not included the polyelectrolyte, if it was not there, the surfactant at the concentrations Michael put in would have come down to this dotted line and the interfacial tension. So the fact that the polyelectrolyte is there adds an additional sink to get more surfactant to the interface. Again, a way to control delivery to an interface. I'm going to go through this really quickly because I want to get onto the second topic, but we did look at the dynamics of this transport. We've done a lot of work on understanding this. On the left is the surface tension as a function of time for a whole lot of different samples. On the right, we've just flipped it around to a normalized surface pressure versus time. That's just surface pressure is just the clean interfacial tension value minus that with stuff on it. So it's this distance. You see it's a two-step adsorption. That's not surprising for polyelectrolyte surfactant aggregates. What's more important here is that we took a single point and pulled a time scale out of each of these curves. And if I plot that time scale versus the effective concentration, I get these black symbols up here. And what's interesting is that if I then put just the surfactants curve, what I'd get for the surfactant adsorption timescales, you'll notice it's exactly the same shape. And the shift here that I've drawn in the arrow is just the difference between the bulk diffusivity of the polyelectrolyte surfactant aggregates compared to the surfactant. All we're trying to claim here is that the timescales of this process are defined by the diffusion of the object in the bulk. And that's not surprising. It's not kinetically limited. In that case, it's diffusion controlled. I don't need to get into that too much else. I can go back if anyone has questions. So what's the processing relevant point that comes from this part of my talk? Polyelectrolyte surfactant aggregates offer us a lot of ways to control adsorption to the interface. The polyelectrolyte in this case could not be dissolved in water. So the only way to get it to an air-water interface through the aqueous phase is to mix it in with a bunch of surfactant and transport it to the bulk. And so the surfactant is controlling the adsorption to the interface. And then you can pull it back off and leave this polyelectrolyte stranded at the interface to control the properties of that interface. So we can make two different kinds of interfaces with a single system, either surfactant coated with a little bit of polyelectrolyte in there, or polyelectrolyte coated with a very small amount of surfactant. And we could control that with the processing. So back to my tableau of different ways we can look at this. The other project I'd like to talk about is the work done by my student Steph Kirby, who graduated a number of years ago, but she did some really beautiful work on particle surfactant systems, and I think it's particularly relevant to this crowd. So this is a model system that had been studied extensively by a lot of different groups. The idea is you take negatively charged Ludox, silicon dioxide. These will be about 22 nanometers. Add to it CTAB, C16, positively charged. Now that's going to absorb on the surface of the silica and impact its interfacial properties. We add a little bit of background electrolyte. So here's some pictures from the literature. These are not ours, but we reproduce some of these. These make phenomenal foams. I think our last speaker probably knows a lot about this. And these are very stable foams. And they make foams only when you've got both the surfactant and the silica in there. Surfactant on the silica on its own won't do this, and the surfactant on its own will make a foam that's not very stable. However, if you look through all of these papers in this literature, you'll see lots of things that disagree with themselves, indicating that these systems are extremely complicated to work with. And so we really wanted to understand what was going on here. For example, these two plots are from different papers where you'll see that the black curve is CTAB, so just the surfactant as a function of concentration, showing that traditional dropping to the CMC and then flat. But mixtures of silicon dioxide and CTAB either show one behavior where it's not interfacially active, or another where it's more interfacially active than the surfactant. Now, there's lots of things going on here. I'm not saying the authors were arguing with themselves. There's concentration effects and time effects. One of the main issues with dealing with these systems is that they're not stable as a bulk material. And so just to show you that, and one of the things that we tried to do to better understand these systems is if you measure the zeta potential of the silica particles as a function of added surfactant, you'll see this very classic curve. When you add small amount of surfactant, it will start to absorb at the silica surface. The silica is negatively charged and hydrophilic on its own. So it wants to be in water. That's why it's used as a thickener. As a pigment. If you add the surfactant, it absorbs to the surface and takes the overall hydrophobicity of the aggregate up a bit and gets rid of some of the electrostatic stabilization. And so what you see, the zeta potential, if you measure it, it will go along as you add more CTAB, and then you'll get to a point where you've essentially charge neutralized the surface. And now you have charge neutralization and a bunch of hydrophobic stuff stuck all over these particles, and they don't want to stay in water. And so you'll see destabilization here. And if you add enough surfactant, you'll actually make what looks like a bilayer on the surface, and you'll flip around the zeta potential and it will have the opposite charge. A lot of work done on the interfacial properties of these things, but I think pictures tell 1,000 words. Here is 3 different lengths, tail lengths of surfactant. The C16 is this middle bunch, and this is what I'm talking about today. The jars are different ratios, right? So it's the same silica concentration, increasing amounts of surfactant. And what you see is at very low concentration, small additions of surfactant, the system is still stable. As you increase the amount of surfactant that you add, you get a large range of bulk instability. The system is actually aggregating and coming out of solution, and it can destabilize back again at the high end where the complexes or the aggregates have become positively charged. Most of the work in the literature has been done in this middle region where you have a lot of bulk instability, and that adds to complications when you're trying to do interfacial studies because you can get aggregates absorbing as easily as single objects. So what we decided to do is work in the area where we still have stability. Now the interfacial activity is very weak here and you have to dig into it, but that's what we did. So we're going to only add about 7 or 8 CTAB molecules per particle, roughly, right? There's some polydispersity in the size of the particles, but this is the rough ratio. And you have to do this carefully, and you have to prepare these the right way so that you don't have everything on one aggregate. So there's a little work went into that, but we're down here where these have negative charge, but just enough surfactant added to it that we hope they become surface active. And they do. If you focus on the blue curve here, this is C16, so CTAB, the traditional surfactant, added to silicon dioxide. These are 22 nanometer silicon dioxide particles. And we have that in solution and we make a new interface. And so these are air-water interfaces. And what you see is the interfacial tension drops. It's not a huge drop. It's about a surface pressure of 10, and then a slow decrease in the interfacial tension. So what we see here is a lot of stuff absorbing quickly, and then slowly more things joining the interface. At some point, at about a surface pressure of 7 millinewtons per meter, we start rinsing the system. So we clear out the bulk solution and allow the interface to do what it wants. Whoops, sorry. And what we see is desorption. Right, so this whatever was absorbed on the interface desorbs, and we get to surface pressures of about 2 millinewtons per meter. Now, this is pretty close to clean, but it's not clean. We can measure down to a 0.5 millinewton per meter resolution in this range. And so if we blow a new bubble here, we will see this jump up to a clean value. So there still is material stuck at the interface, but it's not having a big effect on the interfacial tension. We're not surprised that there's particles pinned at the interface. These are 22 nanometer particles. So if you pick a reasonable value for a wetting angle, you can measure adsorption energies, or you can approximate or predict adsorption energies of thousands of KT. So the particles, once they're on the interface, they don't want to come off, right? And so when we're rinsing it off, probably what we're pulling off is extra surfactant. And so this is our image of what's going on here. We have the air-water system. We have our aggregates in there with their, neat little surfactant stuck on them. We know it's not this simple. We get adsorption to the interface. Please ignore this little guy. He shouldn't be over there on his own, but you probably get some surfactant coming off of the aggregates and adsorbing at the interface. And then when we rinse, what we'll be rinsing out is the free surfactant that desorbed and stuck to the interface, or perhaps surfactant that was on the aqueous side of the silica. But surfactant that was pinned in and around the surface or onto the silica is probably not going to desorb. So again, this surfactant is probably not out in the air phase like this, but these are cartoons. There'll be some surfactant remaining. And so this is the image we have of what's going on in this system. And so we think after the rinsing, we still have particles at the interface. How can we check that? Well, what we do is we actually compress the interface to see if there are particles there. And hopefully these little, these little videos aren't playing. No. Sorry, I'll stop playing with it. Those two videos should show what's going on. If we have the pre-rinse system, when we compress the interface, so what we're doing here is pulling back on the bubble, compressing the interface, we see it come down, and then we see the surface pressure go up rather rapidly, right? But it's still a fluid-like interface. On the rinsed system, what we see instead is the interfacial as we compress the surface pressure goes up rather rapidly, and we actually see the bubble fail. I'll show you that in a minute. I hope one of the videos comes through. So there still is material on the interface after the rinsing, and it's got very interesting mechanical properties when compressed. So what Stephanie did was, for a whole lot of different systems, ran these isotherm or these compression curves, right? So you create the system, get it happy, rinse away the bulk and compress. And we always see this upturn at the end, and it's reversible. There is always a little hysteresis. Over and over again, we can do this. The curves didn't seem to want to be collapsing. And then my colleague, Shelly-Anna, pointed out we should plot these in a more logical way. And so what we do is we plot the local Gibbs modulus, which is the local slope of one of these curves, versus the strain, which is the change in area. Okay. If you do that, everything collapses. The open symbols are when it's been rinsed. The closed symbols are before you rinse it. This is for 3 different tail lengths of surfactants. That in itself doesn't matter. But these curves all collapse nicely when you actually scale them the right way. And this is exactly what we'd expect for a particle-laden interface. And so what we do here is we say, okay, this point where it takes off is a critical surface coverage where the particles are jamming or packing into each other. We don't know what it is because we don't actually have a measure of how much material is on our interface. We know something's there. So if we take models that have been developed for macroscopic particles or particles at interfaces, if you have a randomly close pack, that critical areal fraction would be 0.86. If it's percolating, it's going to be lower than 0.86. So what we did was we assumed this dotted line was at 0.86. We know the radius of our particles. We can do a simple argument for what close packing is. And we estimated from that we have about 1,800 particles per square micron on our interface. Our interface is a couple of thousand square microns, so it's not a small number of particles, actually. A lot of particles still left on this interface. And so if they're stuck on the interface and they're interacting, and as we compress, what we have to realize is that if I've stripped off the surfactant, these are negatively charged. And so if I've plotted this in the two ways. This is where I'm decreasing the surface area and it's taking off. We have some background electrolyte in there. The plot on the right is where I pull out the Gibbs modulus and the strain, plot it the other way. So my premise was that if these were negatively charged, there's going to be a repulsive interaction between them. So if I add some salt, I'll get rid of that repulsive interaction. And then those particles that are stuck on the surface will get closer together. And so what that would mean was that if I increase the salt concentration, the surface area at which I first see jamming should move to the left, right? I need more compression to get the particles to plow into each other. Well, best laid plans, we did not see that. When we added salt to the system, now remember, we absorb the material from aggregates, rinse it off, and then add salt to the system, right? So then do a local screening of what's on the interface. What we saw instead was that it actually took less compression to get these interfaces to go up. And you'll notice this line looks like it has a backward slope. That's because these systems rigidify completely. I'll show, hopefully the video for that will work. What that means if I plot it as Gibbs modulus versus strain is that the curve has moved to the left. And so I had some critical volume fraction or some coverage over here, and it's actually now lower because I've added salt. And so what we are arguing is happening is that the addition of salt screened electrostatic interactions, and we're actually seeing two-dimensional aggregation of the particles on the interface and a percolation of particles. And that's what's giving rise to a jamming-like behavior. If we do multiple compressions, what we'll see happen is if the system is in deionized water, the interface just goes back and forth happily. These are electrostatically stabilized particles on the interface. They can flow around each other and they don't aggregate. We get nice reversible, reproducible stuff, no hysteresis. If we now add salt to the system, and I'll play this, and I'll have to play it a couple of times because this system is now fully rigidified. So on the first compression, which is the first one here in blue, I've changed the interface, and that's why we see a hysteresis. So the first time I've got salt on the system, I push the particles together, they'll aggregate and form a percolated network. I pull them apart, some of them might break up. The next time I try to compress the interface, I've now got these little aggregates or this network on the interface, and it just can't, it'll jam earlier, right? And so this will keep happening until the interface becomes fully percolated, and then the only option for it is to fail. And that's what the pink and the blue curve here are, and that's what this video is showing. I'm trying to compress the system before it compressed happily. Now I've jammed it and created a percolated interface, and boom, now it can only fail. And so I've created a percolated interface that's rigid, but still has lots of areas of free interface in it. And so what's the processing relevant point here is that we can use processing to create rigid interfaces. And there's two steps in that processing. One is to deliver the particles to the interface with surfactant involved and then remove that surfactant. So rinsing steps, which you can control in a number of different ways. And then the jamming, the compressing and the re-expanding to create a percolated interface. And then you can make rigid bubbles and droplets. So the conclusions here from these two parts, I'll just reiterate, but in both of these systems, it's the surfactant that's taking stuff to the interface, delivering the payload. And then it's that payload that's giving rise to the mechanical properties, either the particles or the polyelectrolyte. And we can make lots of different kinds of interfaces. My overall point that I'd like to make is that it is possible to engineer interfaces through either complexing in solution, order of addition, and solvent quality is also a key one. So this is just the interface, is not worrying about the bulk properties. Composition and history matter though, so this is an engineering problem. I should acknowledge the students that did this work. The ones with the stars by their names are the students who've worked on the microtensiometer project over the years and helped develop a lot of our abilities. Funding came from the National Science Foundation and the Gulf of Mexico Research Initiative that was set up after the Deepwater Horizon spill. And then PPG has given us some funding at different times. And I would just like to make a little pitch, since there are students in the audience, if anyone's about to graduate and is interested in a postdoc in Pittsburgh, Pennsylvania, I have an opening for a polymer upcycling project that we've just gotten funded. And with that, I'll stop and I'd be happy to answer any questions if there are any.
Okay. Thank you so much, Lynn. So let's move to the question session.
I'm happy to answer questions in the chat if people don't want to. Oh, there's something.
Yeah. Yeah, Alberto had one. Do you want? Well,
Okay.
maybe Alberto wants to speak. Alberto, you want to ask directly to Lynn your questions? Yes, please open your microphone. You are not allowed. You are not allowed to open it.
Hi.
Oh, hi, Alberto.
Very good presentation. I have two questions. The first one is how is the process to rinsing without breaking the bubble?
It's a good question. So because this is a hemispherical cap and we catch it on the end, we can keep the capillary numbers low during our rinsing process. So we've done a lot of work to get the, when we do the rinsing, we control the flow rate to keep the Reynolds numbers low, and then also keep the capillary number low. So it just comes down to that, controlling the flow rates. If it was a full pendant drop, like at the end, like this way, we would tear it off. But because we've got a hemispherical cap, we're able to keep it pinned at the interface. And so we spent a lot of work trying to get that right. And every now and then we tear one off, but so we're close, but we control it that way. So.
Okay, and then that leads me to my second question, which is how is this method different from the bubble method, the regular?
So
where you do a big bubble, and you measure the Laplace. What's the difference? The real difference?
So the difference is just what we can do with it. You're still measuring Laplace pressure. So we compared a lot to pendant drop and pendant bubble. In those cases, you've got, for one thing, you tend to need several, so maybe almost 50 milliliters of sample. And so we were originally doing this just to get the scale down to make it easier to work with. But fundamentally, it's the same thing. However, with pendant drop or pendant bubble, you're actually using a non-zero bond number situation and fitting the shape.
Yes.
And so we're not doing that. Where gravity does not come in here. The bond number is 0 or almost 0. And so we're assuming you're fitting just a hemisphere to this. So it allows us to manipulate the interface more and do things to it. But the idea behind it, the pressure measurement is exactly the same. For our dilatational measurements, it is a hemispherical cap. So as we do the oscillation, it's not a perfect dilation. It would be better if it was actually a like a sphere. So we do take a hit on that, but we can do things like exchange the bulk fluid. We can manipulate the interface more and not lose it. So it's really just one thing is better for slightly different things. So.
Okay, thank you.
Sure.
Eduardo, anyone else? Anina wants, can you open your microphone, whatever you want?
I will do. Yeah, so thank you very much. Really, really nice work. Thank you. So what I wanted to ask was just on the first part. So you were saying that as you wash the surfactant away, you still get pretty much the same elastic modulus for the surface as before. And I'm surprised that the surfactant doesn't, I mean, I can see why the polymer would be controlling it. I would have thought that maybe the surfactant would help a bit, or it's just in the viscous response that the surfactant would fluidify.
Exactly. I mean, I think so. I'm only showing you the dilatational modulus at a fixed frequency, and so there's a lot buried in behind this. We're not confident in pulling out E prime and E double prime because of some issues with our instrument. So we tend to just stick to the complex modulus. There's a lot of interesting stuff buried in the viscous response. And I do think the surfactant is mainly coming in the E prime or E double prime, the viscous component of this. So I'm reporting just the high frequency plateau. That's why I think the surfactant doesn't come in too much. I think the surfactant is doing things to the mechanical properties, but we're kind of just ignoring those for right now. I'm not confident enough to pull out all of the rheological properties the way we're doing things. So.
Thank you.
Oh, sorry, go ahead.
No, just asking if anyone has any question. But I have a technical question regarding your last experiment where you have a this gel of particles in their interface, and then you see that they drop quite immediately, got stuck and returns. That was very fast. I'm not sure if you're able to see a part of the process using your camera, because you are having actually some data on it, on this process.
Yeah, you mean when the interface fails?
Yeah, exactly.
Yeah, I mean, I think we could put, our camera is not fast enough to see what happens. So it's a complicated process. We can't tell if the interface is failing or if the contact line is just sliding back down the capillary. It's the kind of thing I'd like to take a better look at, but I'm not sure I would do it with our system, right? So if I wanted to figure out what was going on with the interface itself, I would try and create this same situation in a Langmuir trough. Now that we know how to prep it, we could do. And then I'd have a large area where I could look at local failures and better understand, is this like a homogeneous thing, or is this a fracture and a fail?
Because that can be quite inhomogeneous, right? Okay.
Absolutely. And like I said, a couple of our images, it really does look like the entire contact line is sliding back down the capillary. And so that would be a totally different thing, right? So that's why we didn't dive too much into analyzing the failure. I think it's important and worthwhile to look at. And now we understand how to prepare the interfaces. I think we could set them up in a better geometry to study the fracture. I just don't think our geometry is the right way to do it. So
for this particular case, what is the size of the particles or relative to the size of the ball of the?
Oh, yeah. So the curvature of the interface, that the capillary that you're looking at is 40 microns in radius. So it's 80 micron across that bubble. The particles are 22 nanometers. So those are Ludox. So, you know, there's probably on order of 1 million particles on that interface. So they're far smaller than anything we can visualize. So
yeah, of course. Okay.
Yeah, we haven't. So we cut off because our interface is microscopic by design. We want it to be on micron order. So we try not to look at particles larger than 1 to 10 microns, because then we're approaching the size of the interface. So.
So it seems that there's no more questions. So thank you again, Lynn, for your nice talk. And thank you also to Anina, let's say, or two speakers of the morning. So by now we have a coffee break. The session remains open in case you want to discuss, or if there is any other question, maybe there another question from the attendees. So the session will remain open until 11:20 when we start. So roughly in 25 minutes. So see you then, and thank you again to all invited speakers. Oh, sorry, Paco, do you have an announcement or something? Sorry.
Yes, just a couple of one announcement and a request. The first announcement is that please join us on Twitter. The discussions about the posters started now. So, and if you are a participant with a poster, please, I invite you to publish the poster in Twitter and to start the discussion about your work. And something else that I want to request is Isabel will join us at some point from now. She wants to test the Zoom in her office. So I will say something later when she is logged. Okay.
Great. Yes. Thank you.
Lynn, Professor Walker, I have a question. I really enjoyed your talk. Thank you for the results. And I want to ask something about so since I'm, let's say, working with simulation, at some points I work with polyelectrolytes, study polyelectrolytes on bulk and adsorbed in surface, especially with titanium oxide surface. And I study the adsorption of polyelectrolytes to this surface, also with surfactants. And I found really interesting this part where you put these surfactants in the bulk and how they interact with the polyelectrolyte.
Yep.
So since these surfactants are not charged, right? The interaction that you will have in the interface with the polyelectrolyte is just, let's say, some kind of van der Waals attraction, or just dynamic interactions, or what kind of?
So right now the surfactants are charged. So both of the systems I talked about today are oppositely charged systems. So the polyelectrolyte is carboxylated polystyrene, which is negatively charged. And the surfactant is CTAB, which is acetyl trimethyl ammonium bromide. So it's positively charged. So there's definitely a charge-charge interaction in these systems.
I see.
Yeah.
So the polyelectrolyte in the interface are they moving on the interface? I mean, like they are kind of diffusion in the interface?
That I don't know the answer to, but I would assume they are. So I think what we're doing is we use the aggregates to deliver the polyelectrolyte to the interface, because it's otherwise, I don't know how we would get it there. Then it's absorbed. The carboxyl groups are probably sticking onto the aqueous side, but then the backbone and the aromatic groups are probably like right pinned at the interface trying to access the air side of things. Laterally though, there's no reason that the chains wouldn't be able to move, either diffusing around in the interface or, you know, moving on the interface. It's pretty rigid when it's charged, but as you actually absorb the oppositely charged surfactant, you'll get some shielding between the groups, so that the chain could now be somewhat flexible, but pinned on the interface. I don't have any information on sort of diffusion on the interface or things like that. Certainly something that we could measure, not with our technique though. That's one of the, you know, we keep running into the, you know, we can figure out how to get things places and how to control that. But once it's there, we need to move to a different technique to actually characterize what's happening. So
I see.
yeah. So I think there's probably diffusion of the polyelectrolytes on the surface, right? I don't see any reason why not. So
yeah, because from the, let's say, the simulation point of view, that would be interesting in terms of the basic knowledge that you will get in terms. I mean, for example, if you know the diffusion of polyelectrolyte suspension in 2D, you will have some relation between the diffusion and the radius of gyration of the polyelectrolyte.
Yeah.
You know, like this exponent, this critical exponent that would be helpful in terms of basic, let's say, in terms of the chain length of the polyelectrolyte. But I don't know, in terms of a more experimental case, no more applied science, I don't know if this has some implications. You know what I mean?
Yeah, I do. I mean, so we were very interested in the bulk diffusivity and mobility of these aggregates for a long time. It wouldn't be difficult for us to, you know, polymerize in something fluorescent, deliver it to the interface, and then do something like surface FRAP or something to measure diffusivity and mobility. And it's an interesting idea. We published that work, and we've had a number of people reach out to us about it. And I haven't connected sort of the two communities, but I think it would be very useful for us to figure out how mobile some of these polyelectrolytes are at interfaces. And I don't think people know that, or maybe they do. And it might be a literature I don't know. So the simulation world probably has more to contribute to that one, because you can.
Yeah, but actually, that's a question. I mean, it's an open question now, because especially for high concentrated suspensions, right? So because it's difficult. I mean, technically, it's difficult to have a high concentrated suspension of polymers. Yeah. So and study the diffusion is quite complicated.
Right. So I just, we have to look at how we define high, but if our calculations are right, the polyelectrolyte concentration at the interface is actually quite high. It's well above like a two-dimensional semi-dilute. So they're interacting, right? Probably interacting a lot. Actually, it's probably a prime system for delivering the right amount of stuff to an interface and then measuring it. But then you always have to step back and say, I could just take a Langmuir trough and dissolve polyelectrolyte in some volatile solvent, deliver it to the interface, and then make similar kinds of things. And it would be a better way to characterize the kinds of things I think you're interested in. And so I always I'll get just so far, and then I'm like, wait, I don't think our tool is the right way to do this. But I do think those questions are very important. They're important to understanding the mechanics of the interfaces.
Okay.
And then how they make things like foams and emulsions. That's our next step, is to connect it to that kind of thing.
I see.
Yeah.
Thank you, Professor Walker.
Yeah, no, thank you. Thank you. I should have brought coffee upstairs for my coffee break. So
it seems that everyone is taking coffee right now.
Eric, are you there?
Yeah, I just saw the message from Isabel. So do you want to
perfect.
try?
Yes, please.
Okay. So
Yes. Ahora te pongo aquí, Isabel. Chao.
I just promote Isabel to panelists. So there you go.
Isabel,
So,
are you there? Yeah.
Great.
You're mute.
Perfect.
Cool. So welcome, Isabel. Yeah, so you are okay here. So maybe you want to try your presentation and to share your presentation.
Yes, wait a minute. I'm going to close the presentation. Let me see. So you can see my presentation?
Not yet.
Not yet.
Not yet. Okay. I'm going to share. It seems that I completed the window, the completed window. It is not possible. I'm going to put the window only. No, I cannot just share the presentation. I don't know why.
I don't know. Probably, I don't know if you send us the presentation, how it works in these cases, Eric, do you know?
I'm still looking for it.
Wait a minute. Now it seems that I can just share. Wait a minute.
Okay, great.
Now you are sharing your screen. Yes.
Okay, so you can see the presentation?
No, we are seeing the
screen?
The screen of the
Zoom
Zoom.
Screen. I don't know why. Let me see. Let me see now. Wait a minute. I'm going to try another time. No, I don't.
Clear? You want to say something?
Yes, maybe it's because you're using okay, it's working. No,
it's working now.
Yeah.
Okay, I'm going to just put. Now is the presentation. You can see the presentation, and I'm just moving the slides.
No.
You can see.
No, we see the presentation, but just the first page in.
Yes, yesterday I made an example with my son, and it was the same. Wait a minute. I don't know here what. I'm going to try another time. Wait a minute. Es que no me deja. It doesn't let me to share the complete window.
Okay.
Only the window that I have, but it's not possible to see the presentation, all the presentation. I don't know why, but yesterday I made an exercise with my son and there was no problem, but today it doesn't leave me to share.
Probably you can share the PowerPoint and move the slides in the PowerPoint, not in the presentation mode, but just in the edition mode. You know what I mean?
Okay. And what I have to do just to share
you did the same as you did
before. Okay, perhaps now, and I go to the
PowerPoint window.
The PowerPoint. Yes.
So can you click on the presentation mode to see if we now have this mode? Yeah. So can you move to? Yeah. Perfect. So now we have it.
Okay. So the difference. What was the difference? Sorry.
I don't know what you do.
Okay. So now it's okay. There is no problem. Okay.
Perfect.
So I will.
You need to share all your screen or something like that, right?
Okay. Yes, all my screen.
Perfect.
So now I'm going to stop the sharing.
Okay.
And I will be connected, I think, after, well.
Yeah, your presentation is at 12:10.
Okay, moving just in the same way. Vanessa is as attendee, so I'm gonna promote her as a panelist.
And Sonja too, right?
Okay.
Sonja is also in the same session.
Okay, Sonja, great.
So
very good.
I will be here in the panel, and I will just be just in my time when I have to present. Is okay?
Thank you. Great.
Okay, thank you very much.
Thank you, Isabel.
Hi, good morning.
Hi, Vanessa. Nice to meet you.
Nice to meet you too. So
Nice.
maybe I can try to share my screen.
Please.
Okay, so it should be this one. Tac.
Okay, it's in full screen. Can you move to the next slide just to see that it's...
Yeah. Tac.
Yeah,
okay.
Great.
Good.
Great, thank you, Vanessa. Susana, are you around?
You're welcome.
Remember, you are the next chair.
Susana.
It's in the coffee line.
Maybe. Voy a escribirle en WhatsApp. How many people are attending the Congress, the conference?
We have around 60 registered between just attendees, contributed talks, posters, plus the invited speakers that are around 13, if I'm not wrong. So
Good.
we should be close to the 80s, 90s.
Wow. Thank you for inviting me.
Thank you for accepting our invitation.
That's very nice.
So let me just try also Sonja's presentation. Sonja, are you there?
So I stop starting the presentation.
Yes, just give a try for Sonja to share the screen, and then we can just move to your presentation, Vanessa.
Okay.
You are the first one.
I stop sharing my presentation.
Okay, Sonja, nice to meet you.
Yeah, thank you for letting me share my work.
Great. So you want to share your screen just to be sure that everything is working okay?
Yes.
There we go. Okay, so you are sharing your whole screen, right? Perfect.
And then the first slide. And
it seems that it's working. Yeah, it's working.
Okay, thank you.
Thank you. So I also have to WhatsApp Susana just to be sure that she's around for the next sessions as she's the chair. So see you in a few, right? Thank you.
Hello, Vanessa.
Hola, hello. How are you doing?
It's a problem to work at home. Was someone in the door ringing the door?
Okay, okay.
We are still working at home, so.
Oh.
How are you doing?
Yeah. Well, very well.
Are you in France still working at home? Or?
Oh no.
Ah,
we started working here in the lab maybe in June 2020. So
yes, but the students, the regular students in the university?
No, they are in classes, not with the normal. Last year we had a kind of a chair between two students.
Okay.
But this year it is totally normal as we
no,
have previously any distanciation, nothing at all. We will see.
But is nobody infected in your lab? No.
No, they are all vaccinated. That's good.
Okay.
Well, in France, it appears that we are around 70% of the total population and 86% of the population older than 12 years that are vaccinated. So 86% is quite a lot.
Yeah.
And well, the numbers are increasing, but smoothly. We will see. We will see.
Okay.
It depends also on the variation in other countries, because even if here we have a vaccination number that is quite high, in other countries the virus is still being modified, mutating. So we will see. I don't say anything at all. Carpe diem, Susana. Carpe diem.
Well, here just last week, our students start with the vaccination. They were the range of age from 18 to, I don't know, 20 something. Just the first shot, so we are still very delayed, but we're more or less fine. I think we are going to start next week with the half of the people in the university, the presence. But for example, in some schools, my daughter is going a private school and she's attending every day. So depend of the situation of the school. If they have the conditions, or in our case, we don't have good conditions because we have very small rooms and we don't have enough ventilation, and so we are still waiting. So I'm still working from home. That's very boring.
Oh yeah.
Okay. I miss my office.
Yes. Well,
colleagues every day.
You are doing modeling, so.
Yeah, no, I can work from home perfectly.
You can work from home, but I'm an
yes.
experimentalist. So the 2 months, nearly 3 months that we were at home were really, really hard.
No, it was impossible.
Yes.
Yeah. You cannot.
We were writing. We wrote even more papers. It was kind of crazy because Europe or the world was confined, was in the lockdown. So everybody was writing, and we published a lot.
You have time
but it was boring.
Write all your delayed papers.
Yes, that is. Papers that they were delayed for 1 year, 2 years. They were published.
Okay.
It was the positive side, if we have to find one.
Yeah, of course. Okay, yeah. So I think in 1 minute we will start. So I don't know if you are ready already.
Yeah. Okay, so I start sharing my presentation after your introduction, maybe.
I will, yes, I will. Just let me check. Okay, so hello everybody, everyone. So I will continue conducting the session. Our next speaker is Vanessa Fierro, Professor Vanessa Fierro, and she's coming from Institut Jean Lamour from France. And please, Vanessa.
Thank you very much, Susana, for your presentation. I'm going to share my screen. Let's see. It is okay?
Yes, perfect.
Okay. So thank you for your presentation, Susanna. Thank you also for inviting me to your conference. I put this very long title, and summary, I'm going to speak about tannins as a green precursor for carbon materials, micro and mesoporous materials that are going to be used in a wide range of environmental and energy applications, as I'm going to show you. But first of all, let me introduce where I am. So I am in the Rhône region in France with borders with Belgium, Luxembourg, Germany, and Switzerland. And in this Grand East region is, well, we are in Lorraine. We are more or less 2.5 hours far from Paris. And our main laboratory is in Nancy. It was created in 2009 and was the result of the merging of 5 Nancy-based laboratories. We work in about 600 people doing research on materials, metallurgy, plasmas, surfaces, nanomaterials, and electronics. I'm not working in Nancy. I'm working in Epinal in a quite green environment, as you can see. And in Epinal, we have a unique experimental platform, MatterLore, so matter for materials, lore for Lorraine. And essentially, we do porous materials, biosource materials, but not only. We do the characterization and the applications. So we work from natural resources, for example, plant polyphenols, polysaccharides, and simple sugars, and also proteins, to do basic science, for example, surface and interfaces phenomena, chemistry, physics, modeling, and also applied science, thermal insulation or thermal transfer, gas storage, electrochemical storage, catalysis, pollutant removal, either in gas or in liquid phase, electromagnetic shielding, and biomedical engineering. So we are now 5 permanent researchers. Around now we are 8 senior researchers and 4 PhD students of different nationalities. As you can see, we have 2 Mexicans and half women, half men. So let's start with a brief introduction to tannin and tannin-derived carbons. So as you may know, phenolic resins are usually made from resorcinol or phenol. They are molecules of petrochemical origin that they are going to react with formaldehyde. And these 3 molecules, they are really dangerous for environment and also for humans. We are working in some biosource molecules, like these ones, and in particular with tannins that are found in all the vegetal species, and they can be found in fruits, seeds, trunk, roots, bark, leaves. We work with mimosa tannin, and mimosa tannin is in the bark. We work with this molecule. This is the characteristic molecule of mimosa tannin that is a condensed tannin. So these condensed tannins have the same reactivity with aldehydes as phenol and resorcinol, and they can also react with some more friendly, environmental friendly crosslinkers as hexamine, glyoxal, or glutaraldehyde to give resin. They can also autocondensate in very basic or acidic media to give resins. And they can also react with furfuryl alcohol. And these resins are thermoset. And this is very important because when they are submitted to heat treatment, they are not going to melt. They are going to carbonize and they are going to keep the shape. So tannins from mimosa. The mimosa tree is cultivated for 10 years, and the bark contains 30% of weight in tannins in dry bases. And after the barking and by water extraction around at a temperature around 60, 70 degrees C, we concentrate this solution by spray drying. And at the end, we have a tannin powder with a cost around €2 per kilogram. In this powder, we are going to have around 80% of phenolic flavonoid materials, around 5% of water, 1% of amino acid, and the rest are broken pieces of hemicellulose. This is the most characteristic molecule in a mimosa tannin. And we have two rings, a resorcinol ring, and now you understand why it reacts as resorcinol, and a pyrogalol ring. The resorcinol ring is the most reactive one. But let's continue with some materials that we can produce with these tannins. For example, carbon foams. In a typical formula, we are going to use tannin as the base of the resin, furfuryl alcohol as hardener, but also as heat generator, diethyl ether as blowing agent, water as a solvent, the formaldehyde is going to be the cross-linker, and the paratoluene sulfonic acid is going to be the catalyst. And here I prepare a video, okay, that I cannot, okay, I don't know how to start with the video. Okay, but in this video, what we could see is that when we put all these components together and we put the blend into the mold, the foaming is going to start, and simultaneously we are going to have the hardening of the foam. So the secret is to have the hardening of the foam at the same time that we have the end of the foaming. It's like a kind of souffle, to speak in cuisine terms. So with these foams that I couldn't show, but you can observe here the process. After carbonization, that is a pyrolysis at 900 degrees C, we have carbon foams based on different kind of formulations, flowing agents, and foaming methods. And we could obtain foams with, for example, the same density, but very different cell size, or very similar density, but completely different cell size. If I continue with the French cuisine, we can do emulsions. So it is inspired of the mayonnaise recipe. We put the component of the resin, so tannin, the cross-linking, formaldehyde, paratoluene sulfonic acid, and the surfactant, and we are going to start stirring. And at the same time, we put the oil. We are going to do an emulsion that after cross-linking at moderate temperature and extraction of the oil, we obtain a hype. And after carbonization, a carbon polyhype. We can do also aerated emulsions inspired by the Chantilly cream. So we are going to introduce here air. So we are going to have two kinds of pores, those formed by air bubbles and those formed by oil droplets. And finally, if we don't put oil, but we include air, we are going to have aerated foams, liquid foams, and they are inspired of meringue recipe. So after cross-linking and pyrolysis, we have the carbon foam. When we take one of these materials, they are very good as electrodes for the reduction of oxygen in fuel cell. You probably know that the way that we have to promote is that of 4 electrons to produce water. And here you can see the onset potential of our materials compared to platinum. This is very, very similar. And the advantage of our materials is that they have a high stability to methanol and to cycling. Here you can see that when we put methanol, the performances are really constant for our catalyst, but for platinum, it is not the case. If we take now one of these foams and we do different treatments, for example, we dope with nitrogen or with sulfur, we put graphene oxide, we do thermal treatments. What we have seen is that the onset potential for the reaction, it really decreases when the micropore volume is decreasing. And so with the foam, the carbon foam, we have already excellent electrocatalytic properties. Very, very similar to this of platinum. We have done also 3D materials. These 3D materials were done from 3D printed structures in Kelvin cells or gypsum asbin cells. If we submit these materials directly to carbonization, that is thermal treatment in nitrogen, for example, we are not going to recover anything because the carbon yield is near to 0. So what we did is a thermal treatment, a hydrothermal treatment in the presence of dissolved carbon precursors, so tannins, and some additives. And we recover this structure with the resin. And after carbonization, we obtain the 3D carbon structures. And these structures are really useful as photonic crystals. And depending on the cell size, they are going to absorb or reflect the radiation, but they are not going to transmit it. We have done also mesoporous carbon, and I'm going to tell you, maybe you are not familiar with, mesoporous carbons are those with porosity between 2 and 50 nanometers. So we have done carbon gels, carbon spheres, and also other mesoporous carbons, hard and plated. So we use a silica that we impregnated with a carbon precursor, and after carbonization, we have to remove the template. So the hard template route, it is not really environmentally friendly because we are using a hard template that is expensive to produce, and afterwards we have to remove it using very strong acid or bases. So we prefer the soft template route. That is, we use a surfactant to do micelles, and these micelles are going to be a soft template. When we put the precursor, it's going to polymerize around, and when we submit that to carbonization, we recover the mesoporous carbon, because these micelles are not stable at temperatures higher than 400 degrees C. So we have done that by phase separation. We put the tannin with the pluronic in water, we mix them, and after 2 days, we remove the resin form and we submitted that to pyrolysis. And we recover materials that were that had mesopores ordered in an hexagonal structure, and quite nice, as you can observe here. The main disadvantages of these methods are that they require long synthesis times, and also they use hazardous substances. So our objective was to prepare this kind of materials in a one pot and green synthesis and using tannins. So we have developed a method by mechanosynthesis. This is a 1 hour process using only tannin, pluronic F127, the surfactant, and water. We submit to ball milling to form the mesophase, and afterwards to carbonization to obtain the mesoporous carbon. So it is a method that is using only mechanical energy. It is solvent-free or liquid-assisted. It requires short synthesis time, only 1 hour, and few steps. After recovering the mesophase, we submit that to carbonization, and we recover the mesoporous carbon. So we had to optimize the pH, the milling time, and the pluronic to water ratio. Because if we submit tannin and water, here is the nitrogen isotherm at 77 on the solid. This is the pore size distribution, and here there is the cumulated volume. If I submit tannin or tannin plus water, I have essentially microporous material. That means materials with a porosity under 2 nanometers. You can see that here that it is the mesopore range, it is nearly nothing. Okay, and the pore volume is rather low. If I add tannin plus pluronic, I have mesopores that are recognized by this hysteresis cycle, and I can see here mesopores between 4 and 10 nanometers, and the pore volume is increasing. When I include tannin, pluronic, and water, you can see that I have a hysteresis loop better defined. I have a pore size distribution nearly unimodal, and also a big pore volume. It increased a lot. So we need to optimize that. So I maintain tannin in 2 grams, the time in 60 minutes, and I varied the amount of pluronic and water. And depending on the formulation, we have bimodal pore size distribution or unimodal pore size distribution. So in order to optimize the formulation, I deconvoluted this pore size distribution, and I calculated the maximum height of the main peak, the full width at half maximum, and also the peak position. And I represented the maximum divided by the full width at half maximum as a function of the water and pluronic. You can see that the amount of pluronic and water really tailor the mesoporous structure, because when there is a small amount of pluronic, we have essentially microporous materials. When we put a lot of pluronic, the surfactant, we have a bimodal pore size distribution and mesoporosity. So I remind, pores wider than 2 nanometers. And in this area, in this region with the stars, they are materials with a unimodal pore size distribution and quite ordered. But using this contour plot, we could predict that here we will have a perfect order material. We synthesize it, and you can see that this is really very well ordered and with a really unimodal pore size distribution. And this mesostructure is thermally stable, so we carbonize at increasing temperatures up to 1,500, and you can observe that the mesostructure is maintained. Increasing the temperature, what we have is an increase of the surface area, that is due to the increase of the micropore volume, and the mesoporosity is nearly constant, it increased a bit. And doing the Raman spectra, if we represent ED divided by EG and also the full width of high maximum of the D peak, you can see that we are increasing this peak, ED, EG, and the peaks are narrower. So we are increasing the crystalline order, but attention, it is always disordered carbon. We have characterized the mesoporous structure. And for that, I saw this as an example, a disordered material and an ordered material. Both have a surface area around 700 square meters per gram, and the only difference is the mesoporous structure. So we can see that the other difference is the connectivity of the mesopore network. And for that, we have done a scanning of the hysteresis loop for the disorder and the order material. And you can see that they are quite different. So doing a scanning, that means that we do the first adsorption, desorption, and afterwards we start again the adsorption, but now up to, for example, 0.95. We do the desorption, next time is going to be up to 0.9 of relative pressure to the desorption. And like this, we scan really the hysteresis loop. And you can see that we have two behaviors that they are really different. In the first one, in the disordered material, the desorption branch is going to this relative pressure of 0.6. In the ordered material, it is going to the desorption branch. Okay, so this is due to the different connectivity we have in both ink bottle pores, but in the disordered materials, it is indicating open access. That means that we have pores that they are being filled by percolation. In this part, we have a restricted access. We have the same behavior as here. The desorption goes directly to the main desorption branch. Okay. For getting more insight in this connectivity, we have done argon and nitrogen adsorption isotherms in these materials. And you can see that when we compare the nitrogen isotherm and the argon isotherm, we have a first inflection point that is common for both gases, but the second, there is a shift. Oops, sorry. And that means that in the first one, this porosity is being filled by percolation that correspond to pores that they are connected by necks wider than 5 nanometers. In this part where there is a shift, the pores are filled by cavitation. So that corresponds to pore under 5 nanometers. So you can see that in the disordered materials, a part of the porosity is connected by very narrow necks, while in the ordered materials, we have the mesopores and they are connected by very, very narrow pores under 5 nanometers. So we could propose these structures. Okay, in both cases, you can see that there is a low pressure hysteresis, and this is not a experimental error. It shows that there is a slow desorption kinetics. It is because the network is extremely tortuous, and this low pressure hysteresis is fully reproducible. These materials before activation, they are highly hydrophobic. In fact, they are super hydrophobic because we have contact angles when we put a droplet of water. We can have, we are having contact angles higher than 150 degrees. And we can use to separate hydrocarbon from water, as you can see here. When we put the carbon on the tank, immediately the tank is introducing the carbon and the air is pushed out of the material. So they are very good for hydrocarbon removal, for environment application. And we have used also for separating cis molecules from n-hexane to 2,2-dimethylbutane. And the behavior in both materials, in the disorder and in the order, it is really different. You can see that in the order material, the 2,2-dimethylbutane is not entering. So we have compared our material, the disorder and the order carbon with some very well known MOFs, as you can see here. This is the selectivity n-hexane plus 2-methylpentane versus 2,2-dimethylbutane. And here we increase the amount of n-hexane in the gas mixture. This is a logarithmic scale, and you can see that our material, the order mesoporous carbon, is really good compared with this very well-known MOF. So what is happening is that in the disordered materials, the blue that is more or less like the MOF, there is a very well-connected pore structure that allows entering all the cis molecules, while in the order material, we have a pore structure with uniform mesopores, but they are connected to micropores. And so the 2,2-dimethylbutane is not entering the structure. So it's a real molecular shift, this material. We have used, in this case, the disordered materials for the concentration and detention of volatile organic compounds indoor. And so in-house applications, so you know that we have sometimes emission of volatiles because we are using resins for the furnitures. So we have developed a kind of device to detect these molecules. In indoor, we have concentration around ppb, and actual sensor can detect concentration around ppm. So we have developed this system where we have a gas preconcentrator where we put our carbon and we make flow a gas with the volatiles that they are going to be concentrated in this preconcentrator. And after some time, we are going to heat that. So the volatiles are going to be dissolved and they are going to be separated in this GC microcolumn to be detected in the sensor. Because if in the gas we are working with ppb, once we have dissolved, we are already in the concentrations of ppm that can be detected. So we compare our disordered material with a MOF, a very well known, and a zeolite, and we were using benzene, toluene, ethylbenzene, and para and orthosilene. And you can see that our material is really good compared with these porous materials. But it was at 2% of relative humidity. And you can say, well, in these conditions, it's not strange. But we increased the relative humidity to 30 and 60%. And for our material, you can see that there is no change in the normalized response, we can always detect and with the sensitivity these molecules. And you can see the change in their normalized response for the other two materials. And when we increase the absorption time and also the concentration, the response is totally linear. So that is really good. And what it is very good also is that these carbon materials, the disordered ones, they are really stable with time. So we repeated the analysis after 4 months and the response was exactly the same. We have used these materials also, in this case, the order material, for antibiotic removal. And we compare it to a disordered material and microporous materials already synthesized in our laboratory and synthesized by an hydrothermal treatment. So we have a surface area that is almost the same, but a really different pore size distribution. Here is the nitrogen absorption, but you can see that we have this hysteresis cycle. So we have mesopores, and this is only micropores. So normally people establish relationships between the surface area and the capacity of absorption of the materials. Here is the molecule, is tetracycline. And you can see that if we represent the amount absorbed as a function of the BET area, we have a kind of tendance, but the determination factor is not really good. And if we compare with the total volume, the determination factor is much better. So we have shown that the absorption of this antibiotic is more a question of volume than a question of surface, that sometimes it is not accessible. So the materials shown up to now were materials that were non-activated, so the surface area was around 600 square meters per gram. If we want to use them for absorption, for gas absorption, or for energy storage, we have to develop the surface. So we have activated the carbons by potassium hydroxide, CO2, and potassium acetate. The diamonds are our results, and the other symbols are results of the literature. And we have tested our materials for the absorption of CO2. And you can see that the amount of CO2 is practically linear dependent with the micropore volume. Yeah, but this data were reported at 0 degrees C because it's the temperature used for a surface characterization. But in real conditions, we are not working at 0 degrees C, we are working with fumes in the chimney. So we are going to have the smoke is going to be at temperatures higher than 50 degrees C and probably with a lot of water. So in this condition, this very high surface carbon that they were used in other studies published by us also, you can see that the performances are being reduced a lot with the temperature, and also they are high sensitive to humidity. Our materials with a modest surface area but highly hydrophobic could be very interesting for CO2 capture. If we activate these materials, the ordered and the disordered with CO2, activation is a kind of gasification. So we are developing the surface because we are removing carbon, okay? So burn off, that means that we are removing, for example, here, 80% of the material, okay? So you can see already that the for the order material, we need much more time to activate. And this is because we think in the order material, the residence time is shorter than in the disorder material, because we have exactly the same nanostructure for the tannin, for the order material and the disorder material. Here is the Raman spectrum. And when increasing activation, what it is happening is that the ratio DG increases, and also we have narrower peaks because we are simply consuming in priority the most disordered parts of the carbon network. And here you have the isotherms for the disorder and the order materials. And when increasing the activation, we are developing the surface because we are increasing the microporosity that we can measure here. And we are modifying slightly also this hysteresis loop. That is because of the mesopores. But if we compare the surface area, either the BT area of the NLDFT surface, you can see that we have similar textural development with both order and disorder carbons, because we are using the same carbon precursor. And we have a maximum surface NLDFT around 1,600 square meters per gram at 70% of burn-off. And the same is happening for other textural parameters. For example, the mesopore volume, or so higher than 2 nanometers or wider than 2 nanometers, the super micropores between 0.7 and 2, and the ultra micropores under 0.7 nanometers. We have exactly the same tendencies. So with activation, we are increasing the super microporosity and the mesoporosity. But this order mesopore structure, we start the activation process. You can see here for the non-activated materials, surface area around 700 square meters per gram. And for the order material, after activation, so after removing nearly 80% of the material, we maintain the structure. So here is the sectional and the longitudinal view. And we are increasing the surface, we are multiplying by 2. And you can see here also this peak that is indicative of the ordering. So if we want to study the connectivity of the pore network for the series of disorder materials and order materials, we are going to do this scanning of the hysteresis loop. Okay, the first thing is that you can see here that this low pressure hysteresis disappears. Huh? And it disappears because we are increasing the connectivity, so that the desorption kinetics are going to be much faster. And we are going to take slopes at different initial relative pressure, and we represent these slopes as a function of the burn-off and also as a function of the initial relative pressure for desorption. And you can see that for the disorder material, we are increasing this slope, so we are increasing the connectivity in the pores, in the network. However, there is always a part that the slope is not changing, so we have a portion of pore that remains restricted. And we are developing the porosity. Here, as you can see, pores wider than 5 nanometers and between 2 and 5. For the order materials, we have a completely different behavior. That is, these slopes are not changing, so we continue having a restricted access to mesopores with a pore diameter wider than 5 nanometers. And in this part, we are increasing the connectivity. You can see that we can see a completely change in the slope. So we are improving the connectivity, and we can see that because we are increasing a lot these pores between 2 and 5 nanometers. So you can see that we can get really insight in the connectivity of these materials with adsorption of nitrogen and the study of the hysteresis loop. With these materials, with the perfectly ordered, we help those who are developing software for the pore size distribution determination. We have done that with the adsorption of nitrogen and the adsorption of CO2, because the adsorption of CO2 allows the pore size, a more accurate pore size distribution in the narrowest pores. And as you probably know, there is a kind of arbitrary limit in the definition of the geometry of the pores in carbon. Pores under 2 nanometers, they are considered slit pores, and pores that are wider than 2 nanometers and are considered cylindrical pores. And this is completely arbitrary, and it makes here an artifact that we can see here. So this is with the software of Quantachrome that is not considering the CO2, and this is with the software of Micromeritis. You can see here that this artifact appears with both softwares. Okay, so what we have done is to say it is impossible to have this, because we know that our materials, they have 2 separate population of pores, and one is in the mesopores around 5 and the others is in the micropores. So we have moved this boundary and we have said, let's put this limit up to 3 nanometers. And in this way, we have a really logic pore size distribution. So the color is taking into account nitrogen and CO2, and the solid lines are taking into account only nitrogen absorption. Well, after activation, we have used these order materials as electrodes or supercapacitors. So for the storage of energy electrochemically, and we have used aqueous electrolyte and organic electrolytes. In both electrolytes, you can see these rectangular voltaggramograms. And what it is especially interesting is that the capacity retention when increasing the current density. You can see usually people report up to 30. We are reporting up to 80 amperes per gram, and even that we have a capacity retention around 70%. And with cycling, we have a capacity retention of 98 in the aqueous electrolyte and 90 in the organic electrolyte. We study afterwards the effect of the mesopore order in the aqueous electrolyte. You can see that we have, so we use a disordered material and an ordered materials with more or less the same surface area. You can see that in both materials we have in the aqueous electrolyte equivalent voltammograms. If we study now the evolution of the capacity with the current density, we can see that for low current densities, we have the same behavior because the surface chemistry differences are negligible. But when increasing the current density, we can see that the ordered material, it is better than the disordered one. And when we study the resistance, we can see that the resistance in the disordered material, it is higher, probably because we have a slower ion diffusion. With the ordered materials, we have straight channels, so the diffusion is really fast. With the organic electrolyte, we have again the same behavior, but we have here that the disordered material outperforms the ordered one. And the difference is quite high, and for all the current densities, and it is confirmed with the equivalent distributed resistance that is higher for the order material. This is probably due to the higher diameter of the organic electrolytes that produce a reduced mobility in the order materials. Do you remember that we had a narrower pore size distribution? Okay.
Excuse me, Vanessa, we have just a couple of minutes more.
This is enough. Thank you. If we compare now with the literature, you can see that our results are really good. And this is here, this is slightly better, but they were carried out from very expensive materials. And if we compare the capacity retention, so taking a limit of 75%, you can see, for example, here that it is really, really good. The advantage is the very short time for the synthesis, the low price, non-toxic and non-hazardous substances. And as a conclusion, I could say that I hope to show you that tanning is a kind of Swiss Army knife toward porous functional carbons, that we have developed an environment-friendly, safe, and fast method to prepare model materials, and also that tannin-derived materials can be applied for advanced added value applications. So the last application is for the reduction of oxygen in fuel cells. You can see that in alkaline medium, we have equivalent performances to the platinum catalyst. We dope our tannin carbon with iron and nitrogen. And you can see, well, in alkaline medium, it is not so difficult, but in acidic medium, we have also promising preliminary findings. As you can see here, if we compare with this work that was recently published in Nature Communications. But I cannot speak more, and it is best like this because I'm already short of time. Thank you very much for your attention. I open for question, and I wanted to show you this photo because here we have the chairwoman, Susanna, when she was visiting our university some years ago. Thank you very much for your attention.
Thank you very much, Vanessa. Very nice, interesting talk. So now we have time for a couple of questions, please.
It was a quite different presentation from the previous ones.
No, but it's still very interesting. So someone? Well, okay. In the time someone wants to ask something, I would like to ask you a couple of things. I didn't understand very well how do you do this ethane removal from water? You choose the
ethane removal?
Yes.
Well, it is simply we put well, the materials are highly hydrophobic, and carbon materials are used for the removal of hydrocarbons. This is not a secret, but the fact that they are highly hydrophobic makes that they are highly efficient also to separate hydrocarbon from water. And what we could see in the video is that immediately when we put the carbon on the surface, the ethane is entering in the porosity, and it is removing the air from the carbon. It was the bubbles that were on the carbon. So it could be used for removing hydrocarbon from sea, for example, when there is a petrol spill. So it could be used like this. It is a possible application.
Okay. Oh, okay. And another thing, how you say that when you increase the temperature, the order in the crystalline phase increase. How do you think is that? Because I was thinking that it was the opposite. So I don't understand very well why this happened.
Yeah, it happened. Yes, when I was increasing the temperature from 900 to 5,000 to 1,500. It happens because when increasing the temperature, we are removing the more disordered parts. We are like eating the more disordered parts in the order, in the borders. Okay, so finally we are increasing the crystallinity. It is normal, but we are not going to do graphite. We have to keep in mind that this is a disordered carbon. So we are going to partially order it, but we are not going to do a graphite. We are not going to graphitize. No, okay. With some precursor, it is possible to do graphite, but it is necessary to go to very high temperatures, around 2,500. But tannins are not, they are not a precursor for graphite.
Okay. Okay, thank you very much. So is any question?
There is a question in the chat.
Okay.
When you solidify the emulsion or foams, does the structure change during solidification, or are they quite stable? They are quite stable because what we are doing is a kind of curing, and it is this treatment at 80, 90 degrees C, and the shape, it is quite stable. After carbonization, we have a kind of shrinking, okay? Because the carbon yield is around 50%. But during the solidification, it is stable.
Okay. Okay, thank you. Another question? Yes, Victor, do you have the...
Okay.
Yes, please.
Thank you very much for your presentation, Professor Vanessa. I think it's really interesting, the topic. In your presentation, there are a lot of results related with the absorption isotherms, pore side distribution. My question is about the metal organic frameworks.
Yes.
From the theoretical point of view, do you have some results by using techniques like density functional theory or anything related to this kind of techniques?
I work also with MOF. I'm working with MOF also for hydrogen absorption. I'm working also in hydrogen absorption. So MOF, yes, they are materials with a very high surface area. So of course they are interesting. How we are characterizing them? So for sure, we cannot use nitrogen absorption, even if a lot of people are using nitrogen absorption. But as you know, the nitrogen molecule is going to be polarized by the surface area. So it will be much more accurate, that this is what we are doing, to characterize this MOF by argon absorption. So we do that with by argon absorption at 87 Kelvin. For that we have a cryostat, and afterwards it is a bit more problematic because the software we have is the software that was developed for zeolites, and we are applying it, but it is the only software we have. So for sure, I don't know if you are doing DFT modeling for that, but I could be very interested, and I have a lot of data, nitrogen absorption, argon absorption. So I'm open to collaborate because we are working on that, and I'm not satisfied by these models that are given by the Micrometis or Pontachrome, because they are focused on some materials that were very used in the past, and they are still used as zeolites and carbons, but they have not developed new methods for MOFs.
Yes. Yes.
Are you working on that?
Yes, maybe.
We can do, Victor.
Yes, I'm asking you because DFT plus hydrogen is there are assured studies about that. So it's interesting,
Yes.
and it's an open field.
Okay, so I have some isotherm in the most common MOFs. So, well, if you want to start, I can provide that for
Thank you.
any kind of collaboration.
Okay, thank you. Thank you very much.
Good. Thank you.
Thank you very much. So someone else? Well, I think that's everything. There is no more question. So we thank Vanessa. Thank you very much again.
Thank you very much. Thank you for your attention, and thank you for your very interesting questions. It was a pleasure.
So our next speaker is Isabel Sainz. She's coming from the CIP, the Centro de Investigación de Polímeros, I think. Yes.
Yes. Yes.
Yeah.
PPG comment. Yes.
Okay. So please go ahead.
Yes. I'm going to share my screen. I don't know. Please let me know if you can see the screen.
Yes.
Now you can see the presentation?
Yes, yes, we can see. Yes.
Okay, perfect.
Uh-huh.
So, I'm going to put that in.
Yes, perfect.
Okay, so good afternoon, everybody. I would like to thank the organization for inviting me to this Congress. It's really a pleasure for me to be part of this forum. Thank you very much. Well, now I'm going to present myself. I'm Isabel Sainz de Buruaga, and since February of this year, I'm the director of the Polymer Research Center of PPG Comex here in Mexico. I have been in the company, working in the company for 22 years, before 2014 with Comex, and the last 7 years with PPG. So today I'm going to give a presentation about the complex and fascinating world of the paints, how to understand it using innovation and collaboration. I hope you enjoy this presentation. So the outline of the presentation is the following. I will start with an overview about my company, PPG, and the Polymer Research Center. After that, I'm going to talk a little bit about the paints, the composition of the paints, and also some special problems that we are facing in the center. In the third part, I will talk a little bit about the innovation methodology that we follow in our center and also in the company. And I finally, yes, I will finish with the open innovation strategy that we have also in the center. So I will start with PPG. Well, this company was founded in 1883 as Pittsburgh Plate Glass in Pittsburgh, Pennsylvania. Today, PPG is a global supplier of paint, coatings, optical products, and specialty materials. In 2020, it was considered as the #1 company of paint and coatings in the world. So our main vision and our main purpose is to protect and beautify the world. We are around 47,000 employees globally, and in Latin America, we are around 6,600 employees. We have operation in more than 70 countries, and we have been trusted by our customers for over 135 years. Yes, regarding the sales, in 2020, we have around 13.8 billion of US dollars. Yes, 2 product segments drive our business. One is performance coatings, and the other one is industrial coatings. We are also focused in different application of business units. One is aerospace, another one is architectural coatings. We have also automotive OEM coatings, industrial coatings, automotive refinish, protective and marine, packaging, coatings, and specialty coatings and materials. So if you would like just to know a little bit more about the PPG company, I put here the page. You can find more information. And now I'm going to talk or present the Polymer Research Center of PPG Comex. This center was created in 1992 with the main objective of becoming the Center for Research, Technology Development, and Innovation of Comex Groups. Comex is the most important paint company in Mexico. We have now around the 60% of the market in architectural coating, and the center in the center we develop highly competitive products for paint and coating industry. Well, at the end of the 2014, Comex was acquired by PPG, and the Polymer Research Center became the technological pillar of the company in Latin America. Here I have the organization chart of the center. I'm Isabel Sainz, the director, and I'm reporting directly to the Science and Technology Director in Latin America, that is Leopoldo Vilchis. The center is divided in different areas. We have a characterization area with 6 researchers. The responsible is María Eugenia Velázquez. We also have a paint and formulation laboratory with 6 researchers, and the coordinator is Alejandro Zagal. We have an applied science laboratory with 4 people, 4 researchers working there, and the coordinator is José Alberto Olivares. And finally, we have a synthesis and engineering area with 14 people, and we have here 2 coordinators of this area. We also have some people, laboratory technicians, who help us in the experiments that we do in the labs, and we have 14 people. Also, we have an administration area with different departments. That is the accounting with 4 people, maintenance 5 people, and a library. We also have an area for innovation that is coordinated by Lucelen Rincon, and we have 3 people in this department. The CIP head account is around 60 people. So our operation is really fully aligned to the company objectives and strategy. That is the PTPI, the cash flow, the increase in sales and sales for new products, market share. Also, we have some objective in people engagement and successor training, and we have some special objectives in environment, health, and safety process. Our project portfolio definition is based on a strategic road mapping that we make together with the marketing people. And our projects are managed through the stage gate methodology. I will talk a little bit more in the last part of this talk about these strategies. We have internal KPIs, metrics, and we are focused on innovation. That means in the medium and long-term projects. We also have an IP management department, and we also have some external fundings. Regarding the infrastructure of the center, we have different laboratories. The first one is the synthesis and characterization laboratory. We have 3 labs for polymer synthesis, 1 lab for properties evaluation, and 4 labs on analytical chemistry, 1 for sample preparation and wet analysis, and 3 for instrumental analysis techniques. That means chromatography, spectroscopy, and also we have an NMR, is 400 Hz NMR. Also, we have a paint formulation laboratory where we can test all the polymers, the resins, and the additives that we develop in the synthesis area. So here we have the laboratory for evaluation of coating performance. And also we have a laboratory for applied science and technology that is focused in the physical chemistry measurements of colloid and suspensions materials. Also, we have the laboratory for optical properties. And finally, we have a lab with an electronical microscopy. And we have a library with more than 3,400 titles of print books and access to the electronic resources from the Science and Technology Library of PPE. So we can just acquire all the information that we need for the research. Also, we have a pilot plant. This pilot plant is placed in the Tepexpan plant that is near the center. And this plant is fully automated. And we have 2 reactors for emulsion polymerization, one of 500 liters and another one with 80 liters. And also we have a reactor of 80 liters for polycondensation synthesis. And that pilot plant helped us a lot in the scaling up process. So we start from the laboratory scale. After that, we go to the pilot plant and we prepare there all the process in order to go to the industrial scale plant. Our main research lines in the center are the following. I think we are really experts in emulsion polymerization. We develop high-performance binders for architectural, traffic paint, roof coatings, and direct-to-metal systems. We design high-performance additives for paints also, some rheology modifiers, also some dispersants for the pigment that we have in the paint. We design latex particles with control morphology, different kind of morphologies, self-cross-linked systems, high solid emulsions, and some functionalized emulsions. We have some projects also in hybrid polymers, water-based polyurethane, and water-based epoxy resins. Following with our research line, we have a smart or functional coatings. We also we are just working hard in sustainable paints. That means to use bio-based monomers and also recycled materials. And we are developing novel polymer characterization techniques with all the equipment that we have in the center. Here we have some of this work that we have done. Also, we have developed different platforms where we can just have technology in order to be applied in different applications and also in different business units. One of them is the optical properties platform. We also have the rheology platform, energy saving systems platform, and we have done also some studies on drying process of the film. And finally, we are starting a new one, a new platform that is the digital platform, in order to have artificial intelligence system databases and also a machine learning system. And finally, we have a basic engineering area where we have work in simulation, optimization, and control of polymerization processes, and optimization of dispersion processes. Well, in the second part of the talk, I'm going to talk a little bit about the paints, and I will just give some examples of some problems that we have faced in our center, in the CIP. Well, the paint is really a complex system because it's composed by different materials. Yes, we have the resin of binders. In water-based system, we use polymeric emulsions. Here we have. Also, we have the solvent that in our system is water. We have some pigments. Here we have, the most important one is the titanium dioxide. And also we have another pigment to give color to the paint. We use also extenders. We use them to reduce the cost of the paint and also to give some special properties. For example, the mating appearance. And finally, we have different kind of additives as dispersant, coalescent, rheological modifiers, biocides, defoamers. So this is what we have in the paint. In the liquid paint, we can find a lot of interactions between the resin, the pigments, and the additives. And this interaction gives the final properties and the performance of the paint. Also, we have to obtain the best consistency of the application of the paint. And after the application, we need to achieve the best properties in the dry system, as good appearance and protective properties. So one of the most important property that we have in the paint is the viscosity. So if we don't have the right viscosity behavior, we can have different problems as paint dripping or bad leveling, for example. So here we can see the rheology curve that we need in a paint for a good performance. So here we have the curve from viscosity versus shear rate. So if we see this curve, we can find different areas, different zones. In the low shear rates, we need high viscosity to avoid particle settling and also problems with the leveling and sagging. In the second zone, we need the right viscosity for brush application and to avoid spreading and spattering. And finally, we need the right viscosity at high shear rates for rolling and spray application. This is all the curve that we need for a paint. So we have different equipment to measure viscosity in our plants and R&D laboratories. We use the Bluefield viscosimeter in order to test the viscosity in low shears, and that is related to the sag and flow performance. Also in the mid shear, we use a Stormer viscosimeter, and that takes into account the stirring and the mixing. And finally, for high shear, we use ICI equipment, and that gives us an idea of the application field and the spatter. So for a better understanding of the viscosity behavior of a paint, we can use a rheometer, which can give us all the rheology curve. So we can work in a broad range of shear rate. We also can work in a steady state and dynamic system. And we have different kind of geometries. One is the cone plate, another one is the parallel or cylinder. So now I want to explain some viscosity mechanisms depending on the shear rate. So in the low shear rate, we have the following mechanisms in a paint. We have Brownian motion, flocculation, aggregation, chain entanglements, intermolecular association, hydrodynamic volume, and absorption. And in the high shear rates, we can find this mechanism. That is aggregation, intermolecular association, hydrodynamic volume, absorption, and shear interactions. So in order to have a paint with the required rheological curve, we need to use different kind of rheological modifiers. Here I present one of them, is the HEC. This is based on the cellulose derivatives, and the thickening mechanisms of this material is first increasing the hydrodynamic volume of the system, and a second one is with the generation of chain entanglements. So another thickener that we use in the paint is the urethane modifier. That is the HUE, that means hydrophobic ethoxylates urethane. If we see the structure, they are telechetic polymers with hydrophilic and hydrophobic parts, and they are considered as associative thickeners. The HUE, yes, here I have a scheme. The HUE imparts high shear viscosity through the interaction of the thickener with the hydrophobic surface. So the main thickening mechanism is the association between the thickener and the binder and pigment color particles in the paint, as we can see here. Here we can see the molecular structure. We can see the core, hydrophilic core, and at the end of the chain, we can see the hydrophobic parts. In this chart, I present the behavior of these materials in water with different concentration. So we can see that we have any turning behavior in almost all the range of shear rate. And we can see that when we increase the concentration of the hue, the viscosity increase. And if we chart the log of viscosity versus the log of concentration, we can see a linear behavior. Another kind of thickener is the haze. That means hydrophobically modified alkali soluble emulsion. In the structure, we can see a polyelectrolyte backbone, that is this one. Polyethylene oxide spaces, that is these ones. And at the end of the chain, we can, see the hydrophobic groups. Here we have more or less the structure. These rheological modifiers are also considered as associative thickness and present interaction between the hydrophobic components. Here we can see the red ones. Here we can see the interactions that are in these systems. So in the high quality paints, we normally use two kinds of thickness, a haze and a hue. One for low shear rate, that is the haze, and another one for hue, that works in the high shear rates. In this chart, we can see the performance of the hue thickener in a paint, maintaining the haze in a constant value of 1.5. So we can see that the viscosity curve, and we can see that the amount of the hue is increasing in this system. So at low shear rates, we can see that the haze thickener dominates the viscosity performance, blocking the hue action. So if we increase the hue concentration, the viscosity decreases. And at high shear rates, we have the contrary behavior. So when in this part, the hue dominates the performance and start working, given higher viscosity as the concentration increase. So we have the inflection point that is at 33 seconds minus 1. So this is the normal behavior in the paint, just working together with this both rheological modifier. So in this case, I present the rheology curves maintaining the hue fixed at the constant value and modifying or increasing the haze concentration. We can see that as we increase the concentration, the viscosity increase, and it is more notorious at low shear rates, as you can see here. So these polymers have a high molecular weight and form three-dimensional networks, which increases the viscosity of the system at very low shear rates. So one of the most important parameters in the interaction is the particle size of the emulsion or the pigment. So I present here an example of the haze performance depending on the particle size of the emulsion. In the first chart, we have an emulsion with around 120 nanometers. And in the second chart here, I have the behavior of another emulsion with 500 nanometers of particle size. Here we are increasing the haze concentration in both cases. So if we compare the viscosity of both systems at the same haze concentration, that is this chart, we can see that the emulsion with the lowest particle size develop more viscosity, that is the black curve. This is due to the greater number of nodes in the network that have this emulsion taking into account the number of particles. So this emulsion has higher number of particles, and this is why it has more nodes in the system. So we usually just use the rheological or the rheology measurements to solve some problems in the paint or to characterize the paint. So I'm going to explain an example of a road marking paint. The rheology of these systems is really very important because we need to apply the system with a special equipment, and also we have to apply the paint in different conditions of temperature and humidity. So we perform a thermal stability test to assure that we will obtain a good product after thermal exposition. So in this example, we have the rheology curves before and after the thermal stability. So here we have before the thermal stability is the orange one, and after this test is the black one. We can see that the viscosity increase over the full shear rate range after thermal treatment. And we also can see here in the mid shear rate a less persistent structure after the treatment, taking into account the faster viscosity reduction in this area. But still, after the temperature treatment, we can just obtain a workable product with no big changes in its rheological behavior. So in this case, this product is good for the use in our system. Well, in this example, we have the same product, but in this case, we have prepared the paint in different production plan. In one of the process, we have a temperature control during the dispersion process where we add the thickener, and in the other process, we don't have this temperature control, obtaining an increase in the temperature of around 15 degrees in this dispersion process. So the red and the blue lines are made in one process, and the green one was made with another process. So these are different materials, one with one process and another one with another process. So we wanted to know if there will be a problem in the final product and if both systems will perform the same. So we made an experiment with a ramp of temperature, yes, starting from 5 degrees to 75 degrees in a ramp taking 20 minutes. After that, we maintain the temperature in 75 degrees. And in the last period of time, we just make another ramp from 75 to 5 Celsius degrees, also in 20 minutes. So we saw that in the last ramp, we have a different behavior in both products. And the product made without control, that is this one, had an increase in viscosity. So this is due, this increase in the complex viscosity or viscoelastic moduli is due because we can find physical structuring of three-dimensional network due to the electrostatic and hydrophobic interaction. In this case, we have a higher interaction between the particles and the rheological modifier that in this case. And this is only due to the process control that we have in the plant. So I'm going to pass to another example. Another kind of experiments that we do is to use the microcalorimeter to study the interactions between some additives as the dispersant and the pigments, because the system release or absorb heat upon this binding. So in this case, we have studied the interaction between the titanium dioxide and a dispersant. So we performed a first experiment measuring the different enthalpies of introducing water in a sample of titanium dioxide. After that, we measured the change of enthalpy of introducing a dispersant in water. And the difference of the enthalpy of the titanium dioxide dispersant association is the difference of enthalpies of each experiment case. So this methodology, using the microcalorimeter, provide us also with a quantitative method to compare the association energies between different components in the formula, in this case, the pigment and the dispersant, but we can also use that for taking into account the interaction between the pigment and the rheological modifier of the coalescent agent. And this is also a tool to obtain better stability and performance of our system. So in this third part of my talk, I'm going to explain a little bit about the innovation model that we have in PPG and also in the center. So innovation is really an important pillar in our company, and it's also a platform for organic growth and value generation for our customers. So the innovation is focused on our customers and to give real solution to their problems. We are very close with them. Also, this innovation is transversal to the entire organization that allows to optimize resources and to enhance collaboration opportunities. It is also a multifunctional effort. We are working together in this innovation model in order to have the final products. So I'm going to explain a little bit this part. Our process just starts obtaining information from different sources. The first one is our customers' needs. Also, we have information about marketing drivers and marketing vision, supplier vision, and we check also our competence, and we make a technological surveillance. So using all this information, we have different meetings together with the technical area, marketing, sales area, production and logistics, and we prepare the roadmaps. What is a roadmap? It is a strategic plan that defines a goal or desired outcome and includes the visualization of the deliverables in the time, that it is short, medium, and long time. After this exercise, we visualize the project portfolio and we prioritize it, just obtaining all the projects that we are going to follow in the next years. Our portfolio is around 70% of the core technology, around 20% of adjacent technology, and finally 10% of transformational technology. Each project follow a stage gate process that is focused and fast. And after all this process, we have the end of the hopper with the launch of the product or the process, where we have information and technology that goes to the customer, to the suppliers, to the partners, and to the investors. Sometimes we obtain also some technology platforms that can be applied in different applications, and we can just use in different business units. Well, here I present you a summary of the roadmap preparation that we do. The first one is, the first step is to visualize the trends and drivers in the market. So we see the social, economics, technologies, legislation, customer needs, market trends. This is the first step. After that, we have a definition of the value stream that we would like just to give. That means the products, service, cost-effective operation, cost reduction, quality improvement opportunities for customers. That is what we do in this second step. In the third one, we have a division of the capabilities that we will need: technologies, production process, supply chain, procurement, testing methodologies, IP development and protection. And finally, we define the resources: finance and funding, business intelligence network, people skills, competence training that we need, technology R&D network, manufacturing network, marketing network, alliance, supply chain network, and information management. And we visualize that these 4 points in the short, medium, and long term. And we prepare all of our roadmaps in the different business units. Here also, I present the stage gate process that we follow in each of our projects. So we have different stages that we have to follow to finally launch the product or the process. So we start with the concept development. After that, we have 2 steps, one for product definition and specification and planning, and also the product conception and design. This is the second stage. After that, we have this stage of product development. This is the most important one, I think, and also that lasts a lot of time in order to have our first prototypes that we can just go to the scaling up of this process. In the other stage, we have the manufacturing and operation infrastructure preparation. That means to make the scaling up from the laboratory to pilot plant to industrial scale. And finally, we just launch the product of the process to the market. And we have also a period of time where we can just obtain feedback from the customers and also from the market. So in the transition from one stage to another, we have a committee with the different directors from the different areas, the marketing, sales and technology, production, and all the directors that just review the project in each stage. Here we have some gates to pass from one stage to another, and they decide if the project is go or yes, we have to stop this project. We also have here some we have some information about the economical and technological feasibility of the project in order to see or to decide if we can just go further. So our innovation model is a totally customer-oriented management approach. We have a clearly defined objective, unified teams. We have cross-functional teams that has focused plans. We have a lot of information sharing between the different areas. We have teams with decision-making capabilities, focused strategies to achieve the goals, and teams are accountable for profit and losses. We are focused on market segments, and we have the good ideas that we have from the research and development center and from other parts of the company are sought and implemented. And also one important thing for us is that we take risk and take fail attempts to learn and move forward with a more suitable prototype. So for us, it's important also to take this risk, and it's not a problem to fail during the project, because every fail is a way to learn and to have a better product in the future. And also we are using some methodologies for fast forward system in order to go faster to achieve the final goal, that is to obtain the product or the process. And finally, I'm going to just talk a little bit about our collaborative projects in the center. So we are aware that some of the talent required to develop new technologies is outside the PPG, not all the knowledge is internal. And the CIP operates under a scheme of open innovation to develop some new products. So during almost the 29 years the CIP has established working agreements with different universities, national and international universities of institutions. Here we have some examples. We have worked with the Technology University of Eindhoven, also with University of New Hampshire, with Carnegie Mellon University, and with the Polymath that is in Spain. And also we have worked with different universities in Mexico, that the UNAM, the UAM, that they are very well known here in Mexico with different institutions also. So here we have some of the projects that we have worked together with this institution. And the main objective of having this external collaboration are to obtain basic research for the development of new products, also to transfer research results, and to have knowledge or to share knowledge bidirectionally. So this is what we are looking for in this kind of collaboration with the institutions. And also we have been part of different consortiums. We were part of the Particle Morphology Consortium with New Hampshire University, also with for the emulsion polymerization with Eindhoven University in Netherlands, and the polymer synthesis process by living radical polymerization that with the Carnegie Mellon University. We were part in 2007, and also now with PPG. PPG is also part of this consortium, so we can just also have information of this, of Carnegie Mellon University. So the idea of this collaboration in the way of having a consortium is the acquisition of scientific and technological knowledge. That means training and consultancy. Also access to high technological value research results, addressing lines of research, and also priority access and special licensing fees for the intellectual property. And also free use on some of the product. Also we have made some visit to this university or institution to make some training or to have the opportunity to use some equipment that we don't have in the center. Well, finally, I would like just to give an idea of some awards that we have. We have the National Award of Technology in 2007, granted by the President of Mexico. Also in 2009, we have the State of Mexico Award of Science and Technology, granted by the State of Mexico government. And in 2012, we were awarded by the National Award of Technology, especially for a process innovation system, and it was granted by the President of Mexico. And this is my last slide. I would like just to present all the managers and technological leaders that work in the science and technology of PPG Comex, and part of them are the leaders of the center, Polymer Research Center. I would like just to thank this team for the effort that they have done in all the development projects. And well, thank you very much also for your attention. If you have some question, I'm here to try to answer them. Thank you very much.
Thank you very much. It's nice, very interesting talk. So we start with the questions, please. We have one. Paco?
Yes, thank you. Thank you, Isabel. Yeah, thank you, Isabel, for your talk. It was really interesting. And I have some questions in respect to these results that you show about the viscosity of since you said that the paint is really complex, right? And you will have, yes, and you have this basically a polymer melt embedded with water, and with the cross-linkers that basically bond the polymers between them, and also these pigments that basically are like nanoparticles, right, embedded in this polymer melt. And you mentioned this, you call it charges. That's right. So these kind of fillers also in the paint, right?
Extenders, fillers. We have the titanium dioxide and also some extenders that are really big, just comparing to the particles, the latex particles and the titanium dioxide. Yes.
Exactly. So we can say that the paint is basically polymer, water, the cross-linkers, the pigments, and these fillers. No, like let's say basic picture of the paint.
Yes, basic picture. Yes.
Because also, my question is regarding about the effect of all these parameters in the viscosity, because it's very well known that so the cross-linkers modify the mechanical properties of these kind of systems. So I was wondering whether the fillers and the pigments are important in your case. I suppose that the pigment is important for the color of the paint, maybe, no, or the, how you call this, how you protect a surface with the pigments, right? So I don't know if you have some studies in terms of. So I was wondering if these fillers and these pigments has cross-linkers between the polymers.
Well, not well. The paint is really a complex system, no, and we can see also that we have the rheological modifier. There is a competition also with the dispersants that are in the particles, no, in the surface of the particles, and also we have some emulsifiers that are in the surface of the emulsion. So all these materials are in competition in the interaction process. So it's not really easy, but we have a study in pairs, just to see the interaction and the effect, and we have seen some effects that we can just have some ideas. But finally, when you put all the additives on all the system together, there is a problem, because this competition between all the additives just give to a final result that is not the same as when you have only two materials. So we have made a lot of work, and finally we have some studies, but the real life is when you have all the materials and you just work with the haze, for example, haze and hue. This is the most useful system. We have obtained the final knowledge in order to adjust these two rheological modifiers, just working with these particles. And also we have some functional monomers or functional materials in the dispersant that can enhance the interaction from the titanium dioxide, for example, of the extenders, with the dispersant and also with the rheological modifier. So we can also just change the surface of these materials to enhance these interactions. This is something that also we can just do, but we have to change the structure of the dispersants and rheological modifiers also.
Okay, thank you, Isabel.
Thanks, Francisco. Sorry. I think, Susana, you are in mute.
Oh, sorry. Yes. Is there any other question, please?
Yes, I think this is a different talk, taking into account all the rest of the talks. But I think you have enjoyed it, and to know a little bit about how a research center can just work in a private company.
I would like to ask you something, but it's not about your talk, but about your institute. So it's possible that you receive students, for example, for some collaboration or not?
Yes, before we have some programs in order to have students here in the CIP, just working with a special project, because we have to take into account the confidentiality of the projects. So we can just make some basic works, basic research that we can just after that apply to our products. And we have worked together with some institution in order to have students from PhDs or to have master's degree. So yes, we can just have that.
Oh, that's very good. Thank you. Okay, so if there are no more questions, I thank you again for your very interesting talk.
Thank you. Thank you very much.
And we move to our next participant. That is, I don't know if I pronounce correctly, Sonja Richter. I think she's from Germany.
Yes.
Hello. How did you pronounce your name?
Sonja. It's fine.
Okay. So please go ahead.
Yeah, thank you very much for the opportunity to share my work with you. And welcome to my talk about a rotating spherical particle in a continuous viscoelastic medium. My name is Sonja Richter, as you already know, and I'm a PhD student at the University of Magdeburg. And on this topic, I work together with Claudius Deters and Andreas Menzel, the professor in our group. And let's first take a look at the topics I'll address in this talk. First, I'll give you an introduction into active microrheology before I'll tell you how we describe our viscoelastic medium. And after that, we'll take a look on how a probe particle reorientates through a magnetic field and the corresponding linear response function. And I'll close our model with the induced fields through this reorientation and finish my talk with a comparison of our model to the two-fluid model. So I start with active microrheology. Our general setup consists of a spherical probe particle, which sits in a one-component viscoelastic medium, and we exert an external torque to it and monitor the resulting configurational changes. And here we have a little just example. The sphere is subject to a torque and then it rotates. And from the response to the stimulus, the rheological properties of the materials should be extracted. And this is what we know as active microrheology. Next, we want to look at the description of the material. We describe it by two fields, a flow field and a displacement field. The flow field V describes the dynamic state of the material, while the elastic properties are represented by the displacement field U. The displacement field quantifies the remaining reversible elastic displacement that the material element at position R has experienced to end up at this position. Illustratively, this would mean that if the medium relaxed from its current state at time t to an undressed state, the material element from position R would move to the position R minus U. So we can kind of call U a memory field. And this memory field generally decays over time unless the medium is perfectly elastic. We assume a basic relaxational behavior for U in addition to its dynamic driving via the flow field. And this little gamma here sets the forgetfulness of the medium and is the relaxational parameter. If gamma equals to 0, the medium is perfectly elastic and U is just the usual elastic displacement field and all deformations are reversible. And if gamma goes towards infinity, it characterizes the viscous hydrodynamic limit without any elastic contribution. In our description, we confine ourselves to linearized overdamped dynamic of incompressible systems. And in this case, the dynamic are described by a combination of the Stokes and Navier-Cauchy equations. And you can see that the terms that result from the from each of these equations are marked with the same color. And it is also possible to derive this equation from a general continuity equation. In the limiting cases, the original equations can be obtained again. And in this equation, U is the displacement field I introduced before, and V is the flow field from the last slide. And mu is an elastic shear modulus at a dynamic viscosity, P a pressure field, and this F is a bulk force density, which all are parameters that describe the medium or act on the medium. And as we want to look at an external torque, we have somehow to describe the rotation of a particle, and we quantify the rotation by a static rotation vector, which we call omega. The particle rotates around omega with angular velocity w, and we interpret the rotation vector in the same way as we did, or we do, with the displacement field. So if the particle is rotated around omega, it is time t, and if we then stop applying a torque, so the medium can relax back to the unstretched state, the particle would rotate back with minus omega. And of course, the memory of the rotation decays in the same way as the memory of the displacement. So we have an analogous equation here to the one we had with the flow field and the displacement field before. We assume no slip boundary conditions on the surface of the particle. That means that the velocity omega cross r equals the velocity of the there anchored viscoelastic medium, and likewise the rotational displacement of the sphere particle surface points omega cross r is equal to the displacement of the there anchored viscoelastic medium. So if the sphere moves around for a certain amount, then the medium which sticks to the surface has to move the same amount. And next, I'll show you how we describe particle reorientations through a magnetic field. And just to remind you, we want to extract information of the dynamics of the medium from the configurational response of the particle. For this purpose, we want to exert an external torque to them. The practical way of doing this is to look at particles which have a magnetic dipole moment m, which you can see here in this sketch, and expose them to a magnetic field, which then exerts a torque onto them. And the dipole moment we look at has a constant magnitude, so the direction of m just shows us how the particle is oriented. And in this sketch, the particle sits at the origin, so you see that we can measure the angle phi to the x-axis, and we parameterize the magnetic field to look in the z direction. So the magnetic field goes into the z direction, and the magnetic moment, or the magnetic dipole moment, is in the plane of the x and z direction, and then we measure the angle, so the magnetic moment can't move out of the plane. That's what I was missing. And the B field has an amplitude of B cosine omega t, so it oscillates. And from this, we can calculate the linear response of the particle to a magnetic field with small amplitude. And in the following equations, tilde states in rescaled size or in rescaled quantity. So we rescaled most of our sizes with mu and eta, so we don't have to write them out every time. And in the result here, you can see a term which is in phase to the magnetic field, and the other one with sign is even not in phase with the external field. And we here introduce the parameter V, which is just a combination of the gamma, which sets the forgetfulness that we learned, got to know in the beginning, and these two other parameter quantities. And from the results of this slide, we can find the desired linear response function, which connects the angular response that we saw on the last slide to the magnetic field. And we define it as G prime minus I, this is complex I, chi prime prime. And the real part of this times the magnetic field written as a complex with a complex E function. So the real part of this would be just again the cosine we saw before, equals the linear response of the particle. And through a comparison of this expression with the expression from the last slide, then we get the linear response function. So if you multiply these two, you get the real part here, which goes with the cosine in here, and the imaginary part survives more or less if you take then the real part afterwards, if you multiply this with the cosine in here, and then you have that this is basically chi prime and this is chi prime prime. And in experiments, you mostly don't have just one particle, so you use many particles and then determine the induced magnetization along the field direction. And in most cases, it's the easiest way to just average over the angular distribution or the initial angular distribution of all particles. And we assume a low particle density so that the particles don't interact with each other. And in this context, the linear response function is the magnetic susceptibility. Then chi prime is the storage part and chi prime prime the loss part. And in this rescaled version, they both only depend on the rescaled frequency and this parameter V, which we also introduced on the slide before. And this V more or less characterizes the medium if we are closer to the elastic part or rather at the hydrodynamic limit. And these two expressions will be plotted, or this expression will be plotted and this without the 1 over omega on the next slide. And in the upper part here, you can see the storage part of the susceptibility for different values of V. Plotted against the rescaled frequency. And if this is high, so here for low frequencies, it corresponds to more energy storage. And in the lower part, you can see the loss part times omega. So we killed out this 1 over omega. And this high loss part, which we see here, corresponds to energy dissipation. And for an increasing V, so this purple line is here nearly not visible because it's under the green line, but as we go up here to the orange line and here down to the orange line, you can see how we get from the elastic, which corresponds to V with 0, to the more viscous media. And for the different values of V, the shape of the curves is qualitatively all the same. In the limit for a perfectly viscous surrounding, we see that the storage part nearly goes to 0. For all kinds, and the loss part goes here to 1 and also rises for the lower frequency. And on the other hand, the perfectly elastic medium with quasi-static dynamics, so basically omega goes to 0. All energy is stored and nearly or basically no energy is dissipated. And please keep in mind that we are restricted to the regime of linear response. So we only look at small angular deviations, and the amplitude of the magnetic field must be confined accordingly. And the last thing about our model that I want to show you are the resulting fields in the medium. We can directly calculate the time-dependent memory displacements field from the exerted torque and the Green's function, which solves the combination of the Stokes and the Navier-Cauchy equations that I showed you in the beginning. And this is possible to be divided into a spatial and a temporal part. And this is a rather lengthy expression, so I don't show you that, but from the result, we can directly calculate the flow field as it follows from the relaxational behavior. But in the limiting cases, for a perfect viscous fluid, the displacement field vanishes, where the induced flow is in phase with the magnetic driving field, and the other limit is the perfectly elastic medium with quasi-static dynamics. And here the elastic displacement field is in phase with the external driving field. And in both cases, the reaction of the field, so this R cross Y, is just influenced by our choice of the coordinate system. So because we decided to let B go into the Z direction, the field goes into this direction. And the last point that I want to tell you is the difference to the two-fluid model. The two-fluid model describes also a viscoelastic medium by two interpenetrating media. One of them is permanently elastic and describes the usual displacement field, and the other one is viscous fluid, which penetrates this elastic network and is described by flow field. And it's assumed that there's friction between the two media if they move relatively to one another. And this is quantified by parameter big gamma. And from the dynamic equation, in this case, you get the relation between the flow and the displacement field. And this is this one here, this is the diffusal equation. So in this case, the displacement field is conserved. And in our case, we have a relaxation formula for U, so it decays. And the main difference on the technical place is that we assume that we have one component viscoelastic medium, while here we rather have an elastic network and a fluid which goes through it. And by Schmidberg and Stark, they also looked at a rotating particle in a two-fluid viscoelastic medium. And in their case, the flow field vanishes here in this first case. And the main difference is, because I think I have to hurry up a bit, that in a two-fluid state, the static deformation remains, and they have an exponential decay of their flow field, and we have a relaxational decay of our displacement field and a terminal flow, which doesn't decay. And finally, just a little conclusion. We looked at the response of our rigid particle in a viscoelastic medium to an external torque under no slip boundary conditions, and we can use the same formalism for all viscoelastic cases between the hydrodynamic and elastic limit via our parameter little gamma. And we hope that this could be applied to determine material properties by fitting our results to measurement results. Thank you very much for your attention.
Thank you very much, Sonia, for your very good talk. So now we have time for a couple of questions before going to lunch. Yes, Paco, please.
Yes, thank you, Sonia, for your talk. I was wondering about the model of the particle. So the particle is rotating due to this magnetic field that you put in the model, right?
Yes.
and the particle does not self-propel, just rotate due to this external field, right?
Yeah, the particle only rotates because of the external field.
Okay, so in the equation of your velocity field is the velocity field of the fluid around the particle.
Yes, we have a rigid particle, so no fluid inside the particle, and just this is the velocity field and the displacement field in the medium around the particle.
I see. So therefore, what you take into account is both the short distance and long distance.
Yeah, so you can see this picture here. We rotate the particle via this turquoise or light blue arrow, and then around the particle, these two fields arise.
I see. So but the mechanical properties that you can measure of the fluid is just locally due to the particle, not. So what you should expect is that you will have the same response if you use, for example, I don't know, a rheometer. I mean, imagine that you have a box with the viscoelastic fluid, and then you shear the box, so you will have the same effect.
Actually, I don't know. Sorry.
Okay. Because at the end is a way to measure the viscoelasticity of a fluid, right? But locally.
Yeah, we hope that if you somebody would actually do it, they could measure their induced magnetization or somehow get to curves that could be compared to this or the actual unrescaled formulas of this, and then you could determine this V, and depending on what you know of the medium, you can determine the other sizes.
I see. I see. I see. Okay. And yeah, so the size. Just the last question. The size of the particle has an effect in the response of the fluid.
We have. This is probably one of the sizes that got lost while rescaling, because we just set it to A and then calculated with it, and then it doesn't show up here in the results anymore, I think.
Yes.
Here you can see this A to the power of 3, which is in the response.
I see. Thank you. Sorry.
You're welcome.
Okay. Thank you. Well, I think we don't have more questions. So thank you very much, Sonia.
Yeah.
Well, let me ask another one if nobody wants to add something, because this word recalls me to what is doing in what it calls microurology, right? So with microurology, you have particles that diffuse in the fluid, right? So you have a relation between the mean square displacement of the particles and the mechanical response of the fluid, no? And this is how they measure the viscoelasticity of the fluid.
Basically, yes, but
in this case, it's just the rotation of the system.
Yeah, here the particles don't actually move a distance; they just stay in their place and rotate.
So what you measure is a little bit different. I mean, so the mechanism is different, but the microscopic properties that you can measure are the same, right? I mean, are the G prime, you can measure like the G prime or GB prime in terms of the frequency. That's the goal, right?
Mm-hmm. Yes.
Okay, thank you.
You're welcome.
Okay. Okay, we thank you again.
Yeah, thank you very much
for your very good talk. So now I don't know, is there any announcement? Otherwise, we will close this session and we will be back at 4 p.m. to follow with our program. I don't know, is there any, to the organizers, there any, I don't know, any advertisement or something you want to say?
No, Susana, just to remember that the posters are online already in Twitter, and also there is a link in the website. If you go to the poster session link, and you will see a link just on the bottom of the page of the poster session section to see the posters.
Okay, thank you very much, Paco. So then we thank again to all the speakers of this morning. It was very good morning to start our week. And we will see you at 4, okay? I don't know, we leave the session open or we are going to close, right?
Yes, I guess, Sana, maybe it's better if we can close the session and we can
open again later.
Yeah.
Okay. Then see you later. Bye.
See you later, everybody. Bye.